I think we can start. I don't know if there is some of this is working. I think we can start this workshop. So thank you for attending, and thank you to all the speakers for joining us. I'm very glad you're here. And I would like also to thank Levent for organizing this distinguished lecture trip in Italy. So I know that you have already been in different cities, and then we will see the day after tomorrow in Rome, and I think this is the end with Rome ends this tour, this Italian tour. So we are very glad that you passed also by here. And before starting, I would like to invite our director to say some words and thank you. The stage is yours.
Thanks, Cristiano. I'm very happy of this kind of occasion to meet people from every country, and I know very well that are occasion of improving international cooperation and working together of people. So thanks again to IEEE to choose Perugia for the site of this meeting, first of all. And I give you, everybody, my warmer welcome in Perugia, and particularly in the Department of Engineering that I manage since 3 months. The things to do are very impressive. Anyway, welcome again, and I hope the best for the success of this workshop. So thanks again, Cristiano, and thanks again to everybody.
Thank you very much for these words, these kind words. So I think at this point we can start with Okan is a professor of applied mathematics, electromagnetics at Queen's University in Belfast. He is a fellow of IEEE, and he is AP distinguished lecturer, that's why he's here, and serves as an associate editor of IEEE Transaction on Antennas and Propagation, IEEE Antennas and Wireless Propagation Letters, and Open Journal of Antenna and Propagation. He has authored more than 300 articles in electromagnetics imaging, reconfigurable antennas, and metamaterials. He is a UK Leventhulme Trust Research Leader, and Dr. Okay, I think you can start your speech, so the floor is yours.
Thank you, Chris.
Thank you. I don't know, do you need a microphone?
The microphone already attached to my mic, so I will be speaking to this microphone.
Very good.
So thanks everyone, and thanks for joining this distinguished workshop event. And this is my first distinguished lecture talk, so I'm very, very pleased to be here, and I'm very grateful to Professor Levent Sevgi and for this opportunity, also Cristiano for organizing this event. So it's a great, fantastic start for me for this experience. So the title of my talk today will be Met Surfaces in Antennas and Beyond. And I just want to mention that I tried to really minimize the mathematical content as much as possible, because that's not the topic or the purpose of this talk. It's more about introducing what met surfaces are, what we are doing with them, and maybe we can think about met surfaces in the context of not just antennas, but maybe more as enabling technology for other applications. So this is talk to set the scene behind met surfaces as an enabling technology for many, many applications, and also to talk about some of the research that we do in my team at Queen's Belfast, Northern Ireland. So a very brief outline of my talk. I will, as always, I will start with some examples of existing antenna solutions for alternative wave synthesis. The reason why I need to talk about this is because we first need to understand some conventional approaches to understand and appreciate what metasurfaces can do, what they are, and how they differ from conventional wave synthesis approaches. And then I'm going to talk about metamaterials, not metasurfaces first, metamaterials, engineered structures, and then we are going to do a transition from metamaterials to metasurfaces, how they are different, and in what sense, etc. So we'll talk about that as well a little bit. And then we're going to talk about some applications and examples. We're going to talk about some near field and far field applications. And I'm going to emphasize maybe a couple of times, and it's going to sound a bit repetitive, but I think it's very, very important that we appreciate that these structures can be used in the near field and far field. This is very, very important. They enable so many applications, and it's important to appreciate that. I'm going to emphasize this a couple of times through my speech. And I'll give some examples. It will be final focusing, it will be information encoding, computational imaging. This is a major research area for us, computational imaging. Maybe I'll talk a bit more in detail on that. I'll talk about integrated communications and imaging and integrated communication sensing, some other emerging research directions, and then I will finish my presentation with some concluding remarks. And before I go and start a very, very brief overview of our team, we are based in Northern Ireland. Our center is called Center for Wireless Innovation, and that is a center of applied electromagnetics and wireless communications, and we do high-frequency electronics and wireless communications, two sub-teams, and it is home to about 100 academics, engineers, postdocs, and PhD students. And we are the largest physical research wireless research center in Europe in this area. So we have a very strong research focus in both of these areas, high-frequency electronics and wireless communication. So this is what our building looks like, and this is our main campus, Millennium Building. Again, Belfast, Northern. If you ever visit Northern Ireland, if you want to see Belfast, you can drop me an email. I can take you to the main campus. It's a beautiful place. And here I show a couple of pictures, and you might look at this slide and you might say, you know, what are those pictures? They just look like some random pictures. They are not random pictures. They are some pictures from the research that we do in my team. So my group in Central Wireless Innovation, it is called Electromagnetic Imaging and Sensing, and I call it EMIS Lab. So in my team, we do a lot of work on metamaterials, but metamaterials for us is one of the emerging enabling technologies for so many applications. We have different use cases that we look at. We have radar signal processing, we have computational imaging, we have focusing type of applications, antenna type of applications, wireless power transfer, we have deep learning based super resolution. So these are some pictures from our work, and I very crudely here drew a line. So this line here is the region that I'm going to focus on in my talk. So only this part. I'll do my best to sum it up in about an hour, and in about 45 minutes, 50 minutes, to talk about this part of our research that mainly focus on metamaterials, metasurfaces, as antennas, and beyond applications, just to set the scene. And this is my team, Electromagnetic Imaging and Sensing Lab. These are some of our facilities. These are our group members, PhD students, postdocs, research engineers. So we have a very large team, and we are again looking at different aspects of applied electromagnetics on imaging, particularly by using metamaterials and metasurfaces as an enabling technology. All right, so the first bullet point of my outline was conventional beamforming approaches. So we need to look at conventional antennas, and this is the antenna part of the talk, in terms of how we can do beamforming and what are their challenges, so that we can understand that there's a need to address some problems. Otherwise, there wouldn't be a need for a solution. So if you look at literature, very generally speaking, the two most widely used approaches for beamforming can either be understood in the context of mechanical type of scan or all electronic systems. For mechanical version, we have mechanical scan antennas. A perfect example of that would be a parabolic dish. You might have all seen this type of antenna, very, very big antenna, and kind of curved metal sheet. And you can scan it mechanically, and you can scan the radiation pattern of the antenna like using that kind of scan. And we have here a quasi-optical system. So it has a mechanical scan mirror, and then you can scan the mirror, and the projection and the secondary reflection, it becomes scanned as well by means of mechanical movement. And this is a slot array, and you can scan the platform here, and then by doing that, you can scan the radiation pattern of the antenna. These techniques work very well, so I'm not going to stand up here and say that these approaches are problematic in terms of the radiation pattern performance or side lobes, etc. They can meet most of the metrics required depending on the use case scenario we talk about. But if the criterion that we have is about speed, is about power consumption, is about the form factor, they might not be the best solution. So we might be looking at some other approaches for this. So they are slow and they are bulky. So generally speaking, we don't want these problems. They are bad for us. The solution to these problems can be all electronic operation. So there's nothing mechanically moving here. And the best approach for that will be phase arrays, what's called phase arrays, all electronic antennas, all electronic scanning platforms. You can see here maybe thousands of antennas we have. These small circles, they are antennas. And here we have square type of patch antennas here, you can see. And here we have the array slot type of array. But the idea is that each element, or a subgroup of them, they are connected to what we call a phase shifting circuit, a set of power amplifiers. So the hardware complexity can grow really, really quickly with this kind of structures. They can be really complex, and they can be very, very power hungry. So we don't want these problems either. We like the all electronic approach because it can be really, really fast, electronically scanning the beam, but these are big problems for us for certain applications. So these challenges here, the intersection of these challenges, I think set this in very nicely for an alternative approach. In this case, metamaterials and met surfaces. There's a need for that. If the use case scenario that we have in mind needs to be fast, and it needs to operate under very low power constraints. So these are one of a few criteria that we are talking about here. So under those conditions, we might need another approach. And the first thing we need to talk about is metamaterials. So we are not jumping straight to metasurfaces. Metamaterials, they are three-dimensional structures, and we are essentially mimicking atomic response at lower frequencies. You can think of it that way. So what we have here is a three-dimensional structure. So this structure is a three-dimensional structure, or this structure is a three-dimensional structure. We can think of it that way. And then you can see here these small circles. They are what we call meta-atoms. And they're very, very small in size. Electrically, they are very, very small. Lambda over 30, lambda over 40, lambda over 100. There are different papers, different periodicity requirements. But the bottom line is they can be really, really small. And under those conditions, we can homogenize this kind of structures. So this is a three-dimensional structure, again. And if these structures, these meta-atoms, are very, very small, then we can make the assumption there's a homogeneous structure, and then we can calculate an effective mu, effective epsilon, effective permittivity, and effective permeability based on that. So we are kind of doing a homogenization procedure, and then we can synthesize a different media like this with different epsilon and mu responses. There's a three-dimensional structure. We can do some other things. For example, there we'll talk about invisibility. So this is an invisibility cloak at lower frequencies. So we can do transformation optics. We can design it in such a way that the wave can be coming in, and by the time it leaves the structure, it will be as if the structure wasn't there. So there'll be no reflections, and it will be all transmission. So it will be, again, the structure wasn't almost there. So that is the principle of invisibility cloak. And we can design three-dimensional structures again. We have here a depiction of that. We have a patent application back in 2023. So we eliminate this structure with a reference wave, and we split the beam. We can do so many things. I'm going to talk about this in more detail later on. So these are some examples from the patent application that we had also. This is the three-dimensional volumetric hologram, and we can focus the beam, we can scan the beam, we can split the beam, and this is a depiction of what it would look like in practice. So these are the metamaterial elements. We stack them in a three-dimensional grid, and because electrically the elements are very, very small, each of these elements, we can homogenize the response of that, and then we can synthesize this kind of different functionalities. So this is what we call holographic operation. Again, I'm going to talk about in more detail in a couple of slides after that. So that is metamaterial. It's a three-dimensional structure. So we have a volumetric structure that enables us to do different things with electromagnetic media. And their projection onto a planar structure, or it can be conformal structure as well. And so we are compressing the structure in one of the directions here, and we're collapsing the third dimension, essentially, into a two-dimensional structure for this example. It is called a metasurface. So the definition, depending on which group you ask, you might get a different definition for a metasurface. Some people, for example, don't consider frequency selective surfaces as a metasurface. Some groups do consider that. It really depends, I would say. I'm not going to give here a unique global defined definition, but one common feature I will mention here is we have sub-wavelength elements, and we are synthesizing using these sub-wavelength elements an electromagnetic response in transmission mode, in reflection mode, or combination of both. It can be done. So the idea here is we have a holographic metasurface. Again, I'll talk about that in more detail, but we are exciting this structure using a surface wave, and then we are using the metasurface layer. So these pitches here, they are metamaterial elements or meta-atoms. They interact with the surface wave, and what comes out is the radiation pattern of interest. There's no phase shifters here, there's no power amplifiers. This can be done using purely semiconductor elements. And so what we're eliminating here is this kind of architecture that I just talked about in phase arrays. So these are phase shifters, these are power amplifiers, these are antennas. We don't need a dedicated biasing or feeding line for each of these elements. We can eliminate this kind of structure altogether. Instead, we have pin diodes or varactors, and we can tune them, and we can scan the beam that way. So it's much simpler, at least in my view, to do this kind of modulation. And so this is a typical description of a metasurface. We have a microscope transmission line here. We have what we call complementary ELC unit cells. We have pin diodes, and we are tuning them on and off, and we are scanning the beam by doing that. It's a single layer structure, and this can be as thin as even 500 microns. I'm going to show you an example of that later on. So in this example, for example, we have pin diodes. We can tune them on and off, and we can get a different response depending on the element modulation pattern. If it's on, we get this kind of radiated power. You can see if it's off, the element, then we have no radiation coming out of this element. So that means that we have full control in terms of how these tiny elements radiate in free space. We can tune them on and off just by controlling pin diodes in this particular example. So this slide used to have a lot of equations, and I removed all of those equations. There's no equations here, and I will try to explain this in, I think, words. It's better to do it that way. It's actually a very, very simple principle. It is holography, and I'm sure we all hopefully play with some optical holograms. So the idea is that you have a certain pattern etched onto the hologram, and you look at the hologram, you turn the hologram to different angles, and you see different pictures from that hologram. So it's very, very familiar concept for us. It is the same concept. The only difference is that it's not at optical frequencies. It's at microwave, maybe a millimeter wave, maybe terahertz frequency. So we are going down in frequency. The idea is the same. So all we are doing is we are starting with a reference wave. So it can be an antenna like this. We might be exciting this antenna in the center using a monopole feed, or it can be a two-dimensional aperture like this, and we might be exciting this antenna using an H feed, or it can be any type of other structure. It doesn't have to be this type of form. But here, in this example, we have a square element, the structure. We are feeding this element at the H, and we are launching here the cylindrical wavefront, and that becomes our reference wave. And it's essentially a game, and the game is about taking this reference wave and modulating it in such a way that we are going to get this aperture field distribution. So this is our object function, the one on the right, desired aperture field, and we want to get from guided mode, reference wave, to the desired aperture field distribution. So we calculate this, we know the far-field pattern, we can do a backpropagation of the far-field pattern onto the aperture, so we know exactly what the field distribution should be on the aperture of the antenna. That's our object function. And on the other side, at the bottom, for example, we know what the input is. Input, output, we interact the two. That is, we calculate an interference pattern. And that interference pattern is the metasurface. It's hologram. So from the same principle of an optical hologram, if we eliminate this hologram, the metasurface, using the reference wave, it's bound to produce the object function. It has to. Mathematically, that's how it works. So it's actually very, very simple. Two-step process. We code the guided mode, we code the object function, and after that, as a quasi-step, interact to calculate the interface pattern, and that becomes our metasurface. So, yes? Yes.
On a certain distribution field on the aperture, and that distribution field on the aperture is referring to the pattern where you want to scan.
Yes, that's correct. Yes.
So that's the things of the hologram. The hologram is the distribution fields on the aperture.
Yes.
And looking that you can create different.
Absolutely. Yes. So the guided mode doesn't change. It's the same guided mode and the way feeding to structure. What changes is the desired aperture field. If I want to scan the beam in this direction, I have a different projection. If I want to scan the beam in that direction, for example, I have a different projection. So it tells me basically what the field distribution should be, and that is changing. I interact the two, and then after that, I might be calculating an amplitude pattern or the phase pattern or combination of both. I know exactly which elements I should be turning on and which elements I should be turning off, and I just use pin diodes or varactors to be able to do that. So the procedure that you mentioned is exactly right. And when I talk about this previous slide, people think that it's just an academic idea, it hasn't been realized, you know, it's maybe a speculative idea. It's really not like that. I wanted to mention that it's actually an established technology. We have verified this concept practically in many, many other groups. There'll be also a talk in Rome in metasurfaces. We're going to do another district lecture event there, and Stefano Macchi's group and the others group, they will be giving their presentations as well. So there are plenty of works out there. So here is the theoretical paper that we published back in 2017. we set some of the physical constraints around that idea. So we can do a binary modulation, we can turn the elements on and off, very, very simple. We can scan the beam, we can do grayscale modulation. So we're using varactors in that case, and then we are changing the amplitude coupling strength, not just ones and zeros, but intermediate values as well. That gives us a better control at the expense of slightly increased hardware complexity, and we are looking at phase modulation here. So we can do that as well, and that gives us the best response. It's a bit more difficult to do that, but it can be done. So this is the theoretical foundation, I would say, behind the idea where we establish the physical limits of this idea. And then going forward, we design so many metasurfaces. So this is just one of the examples. This is a two-dimensional metasurface. And you can see that the atoms here, they have a cross-shaped distribution, horizontal slot and vertical slot. The idea behind this structure is that we wanted to encode two different sets of radiation patterns, and each of them has three main laws. So it's three-beam pattern, horizontal polarization, and then three-beam pattern, vertical polarization. So you change the polarization, and you look at different polarization bases. You're essentially doing, in that case, polarization multiplexing onto the surface in the far field. So that's one particular example of doing that. And we have done also near field focusing, and we've implemented this in the context of wireless communications. So the idea is that we can do focusing, or we can do a complete random beam synthesis. There's no focus here whatsoever, and we can define a threshold of the receiver, and then by using the threshold level, we can do a very simple on-off based modulation technique here. So wireless communications community, they were very, very interested in this idea. It's something we already very well know, but for wireless communications community, they were very, very interested in this idea. They were very surprised actually when we showed these results to them for the first time. So this is another metasurface example. That's a cavity-backed metasurface. It's doing near field focusing and in two different polarization bases. Polarization 1 focusing at one depth, distance. Polarization 2 focusing at another depth, distance in three-dimensional space. And it's not just academics verify this concept experimentally. There is a company, and there are many, many companies. I'm not here to advertise any company, obviously, but there's one company called Kymeta, and they are based in Washington, Seattle. They validated this concept for industrial applications as well. They have many, many different products for different applications, similar to other companies as well. So this idea here, you can see this picture. This is what's called antenna. This is one of the product ranges. The structure has about 6,000 mathematical elements, and they're tuning the radiation pattern of the antenna by turning these elements on and off in this example using pin diodes, or in this case, a different technology using liquid crystals. The latest version that they have, they're using varactors. So there are different technologies for different applications. And you can see here, by tuning the element distribution, they can scan the beam in another direction. This is a fully commercially deployed technology. And the reason why I'm showing this slide is because, again, I want to maybe break the perception that this is an academic idea, which is not a bad thing, by the way. It's a good thing. The curiosity starts at that level. We have to start from there. But I just want to make sure that we also appreciate that commercially it's a validated technology as well. So the technology is out there. We're not talking about some air-fair idea that's already validated, used by different companies, etc. So TRI level, technology readiness level discussion, we are talking about very high TRI level here. So technology is commercially even available. So this is the antenna that we developed. For example, it's a one-dimensional metasurface, and we have here pin diodes. We have tiny elements to the metasurface here. We tune them on and off, and we can scan the beam beautifully. You can see that the red elements are off, green elements are on. All I'm doing here is that I'm doing the calculation of the object wave. For each radiation pattern, I have a different projection, and then I do the calculation of the interference pattern. Based on the interference pattern, I turn this element on or off, very simple, and then I can scan it. So these are some examples that we did. Again, far-field application, we can scan the beam. Of course, we had a lot of mathematical models. So this is one of the nice things to look at. In the background, there's a very, very big line set of code, which is the ugly part. But here we see the results. So you can see the mathematical elements, those dots. We are looking at the distribution, the element distribution of them, the excitations, and we can scan the beam. So this is where the research begins, with the fundamental understanding. And then after that, we fabricated this kind of structures. I'm going to talk about this structure a bit more detail next slide. And not only far field, again, as I mentioned before, but in the near field as well. These structures can manipulate electromagnetic waves across the entire electromagnetic spectrum, far field, near field, very, very important to appreciate that. So different applications fall into different parts of the electromagnetic distance from the aperture. So this something is very, very interesting in my view, and the reason is that this structure is the world's first 3-5 compound silicon gallium arsenide reconfigured surface antenna. We developed this structure in collaboration with NASA's Jet Propulsion Laboratory, and we launched this antenna as part of a remote sensing mission. So this is not just a lab-based demonstration, lab-based measurement. It was launched as part of a mission. So what we have here is only a 500 micron thick structure. So this is the metal surface. You can see it has 3 ports. And depending on which port we do the excitation from, we can scan the beam in the XZ plane, YZ plane here, this horizontal cut. And we had to place this structure on a metal sheet, not because it's part of the design, but because otherwise we couldn't measure the structure. It was so fragile. If you touch the structure, it breaks down. It's that fragile. So we had to mount this on a big metal block to be able to do the measurements. So again, 500 microns thick, world's first 3-5 compound reconfigurable double-band metal surface. And we did the characterization, we did these measurements, and the results were pretty good. So we're very pleased about those results. This is the radiation pattern in the both side direction. This is the radiation pattern when we scan the beam in the YZ plane. It's about 15 degrees. So it does what we intended to do with the structure. And it's on gallium arsenide, silicon gallium arsenide substrate. The idea behind this is that we could also grow diodes, Schottky diodes, directly onto the substrate. So if you do that, then not only we can scan the beam in the YZ plane by switching between different ports, but we can dynamically tune the metal surface to scan the beam also in the XZ cut here, this vertical cut. So that gives us full 3-dimensional control in free space. So that's the idea behind the gallium arsenide silicon compound substrate. So the idea works like this. So you excite the Schottky diodes under different biasing voltages, and then you can tune their transmission properties. And if you can do that dynamically, then for this design, you can also modulate the transmission response of the surface by doing that. Yes?
What is based on your experience, the operating range of this kind of technology?
So can you repeat the question again?
The temperature operating range of this kind of technology.
Frequency or
Temperature.
temperature? So for this one, it is dependent on the substrate itself. I believe that for this structure, we are good to even test this under extreme space conditions. This gallium arsenide is a special type of substrate that was engineered specifically for that reason. So you can go, I believe, above minus 56 Celsius, all the way up to plus 100 Celsius, those temperatures. But anything beyond that, we need to do a bit further refinement in the substrate structure. So there is also another reason why we couldn't simply use what we call Rogers type of substrates or some other dielectric substrates is exactly because of that, because it had to be launched for the mission that I talked about. It had to survive in these kind of conditions. So that's one of the reasons also why we had to specifically engineer this kind of substrate.
And for space, the EV ions is not a problem.
It's not a problem. For the structure, it's not. So before we launch this, we do all the vibration tests, all the EMI tests, all the temperature tests. Only after we verify that it works on those conditions, then it can be launched. Yes. Any further questions? Or? Okay. All right, so we are still in the antenna part of the discussion. We are in the far field, and we talked about specifically a little bit in the near field as well. So, as I mentioned, we are not the only group working with surfaces. And there are many, many other examples done by others, Stefan Maci's group, so you can see here, they've done some amazing work in this field. They are one of the pioneers in this field. So you can do different modulation techniques, you can synthesize different patterns, and you can scan the beam. So these are different examples. This is just to give maybe an overview of some other works as well. And there's a lot other works as well. So it's not possible to capture all the others, but just to give a good sense of what is also out there. Polarization control can be done, as well as beam scan. So this example is interesting. Maybe I'm biased because it's our work. And this is a collaborative work that we did with the University of Limoges in France. And this is where I'm going to focus now a little bit towards near field as well as far field, because this structure can do both types of beam synthesis using the same aperture. So what we have here is a metasurface. It's called what we call Twins metasurface, because we're using Twins diffraction reaction principle to synthesize this kind of modulation patterns. So we are radiating two different sets of patterns depending on the modulation that we do. We can radiate a CP type of radiation pattern, and we can encode different directions into the radiation pattern. So we have here left-hand circular polarization and right-hand circular polarization. So in left-hand circular polarization, we have broadside radiation, and right-hand circular polarization, we have nothing. So we are doing here polarization isolation. The antenna specifically radiates in the left-hand circular polarization base. And we can also do different polarizations radiating in different directions. So left-hand circular polarization radiating in this direction, right-hand circular polarization radiating in this direction. So we're doing polarization multiplexing. And we can encode information onto the surface in the near field. And that information can be much more complex. Not just radiation patterns that we are talking about here, but even certain shapes, certain letters, certain words can be done. So here we have far field. These are radiation patterns. And here we have near field information. So for the sake of simplicity, we encoded two sets of information here. For left-hand circular polarization, letter L. For right-hand circular polarization, letter R. So we can do this kind of things, and depending on what type of information we want to encode, far field and near field, we can modulate the metasurface accordingly, and we can encode this kind of patterns. So the bottom line here, I think, is very, very important. We are not limited to far field. Some people make this assumption. It's not a wrong assumption. It's actually, in my view, an incomplete assumption that it's a far field design. Yes, in a sense it is. We can do far field beam synthesis, yes, but equally important that subwavelength sampling enables us to do so many other things, including information encoding in the near field, certain shapes, etc. So one thing we can do, for example, using this kind of structure, is we can use this as a key for wireless communication, secure key, to this physically security for us. So unless you see this kind of certain set of information, you don't start link, you don't start communication. It becomes part of the physical security. So things like that can be done. And in the interest of time, I will speed up a little bit. So this is again another example. So we have a near field metasurface here, and what they did here is an example from a group at Duke University. I used to be there before I joined Queen's University Belfast. So the idea is that we have a metasurface, We can encode different types of shapes, not just letters, obviously. So we have here the fabricated matter surface, and using the holography principle, if we excite the matter surface at different frequencies, all we are doing is we are changing the frequency. We can get a different shape at different frequencies. At 79 gigahertz, we have a circle shape. We change the frequency. At 88, we have a square. At 97, we have a triangle. At 106, we have X. So we have 4 object functions here. Object function 1, object function 2, 3, 4. For these, we combine them, superpose them, and this is a superposed matter surface. And we are doing a sweep, and at each frequency, we are measuring the specific shape that we want to get. These are measurements, these are simulations, and you can see that they is pretty good. So it works. So another example, what we can do with these kind of structures. So we are not limited to beam scanning or beam forming in the far field. We can do so many other things. Near field, another example, this is a collaboration that we are doing with our colleagues in Korea, Yonsei University, University of Limoges, and Duke University. The idea is that we can focus to beam. We can do, for example, focusing on multiple beams. We can do focusing on 2 beams, again, at different amplitudes. We can focus to beam, and then we can change the position of the focal point in the near field at different frequencies. And what we are showing here is we can predict the response of the structures using semi-analytical models. This is one of the challenges that we have in this field, is that we have elliptical large apertures, matter surfaces, deep subwavelength sampled. So we are talking about a lot of elements. And modeling these structures using full wave programs can be difficult. When we need to do optimization, it might take maybe days. So we don't want to rely on full wave solvers. Instead, we develop quasi-analytical models in which we start with a unit-cell response, meta-atom response, and then we rely on analytical models to predict the overall response of the antenna, and then we do the optimization analytically after that point. It becomes much quicker to do that. You can see the agreement. CDM is coupled dipole model, and CST is a full wave solver, and we're getting reasonably good agreement between CDM and CST. So that enables us to do this optimization much faster.
Can you go on slide before?
Yes.
Before. Okay, goes before that. Okay. What kind of bandwidth you are able to achieve with this kind of, because they are not the resonant element, right?
Yes. So it depends. You can use a resonant element. You can use a weakly resonant element. So if it's not strongly resonant, you can widen the bandwidth a lot more. If it is highly resonant, then the bandwidth can be really, really narrow. So there's a trade-off there in terms of the aperture efficiency, in terms of the bandwidth, etc. So for this structure, there is a single frequency design, because we want to operate at a particular frequency to be able to do that.
About the antenna
Yes, it can be wideband, but then we are talking about the trade-off there in terms of aperture efficiency, in terms of other parameters as well. So I will show some other examples. For example, we have about 8 gigahertz bandwidth in the entire K-band. For this design, it's a single frequency.
Yeah, sure.
Yes.
The application is different.
Different, yes.
Okay. The only things that I can maybe not so in depth the math. What's not so clear to me is how you are able to scanning, turning on and off.
Yes.
Different elements, how this happens. It's like magic. For me.
It is. So it's all about the change in the object function. Remember, I talked about the object function. If you change the frequency, then your object function will also change. Your reference wave will also change. In that case, the model is the same model. Mathematically, we are not changing anything. The wave definitions are changing. So when you interact the two, the pattern is changing. That is the hologram. So all this changing is basically, instead of having an element on at a particular point, I might have an element on at a different point now. Once I do that interaction. So all is changing is the description of that reference wave. I guided mode. Mathematically, everything is other than that. Yeah. I'm happy to have a chat later in more detail. So it's really not that complicated in the way that we are doing this modulation. The beautiful thing about this structure is actually it's the simplicity, I would say.
Yes, understood now.
Yeah. And I want to very briefly touch upon the configurable intelligent surface as well. So it's a very, very hot topic. And the principle is the same holographic modulation. So depending on the sample requirements, you might think that this is a metasurface or this is not a metasurface. It really depends on the sample requirements and other structures as well, other parameters we're talking about. But the holographic synthesis is the same. So we might have a reconfigured surface, two-dimensional structure. We might be eliminating the reference wave from a base station, for example. And we have an object function. We interact the two. And then we eliminate the structure with the reference wave. It's bound to produce the object function. The same principle. So it can be reflection mode. It can be transmission mode. Very, very important in my view that it's not just reflection-based operation in the configured intelligent surfaces. They can operate in transmission mode as well. So sometimes people also assume that this is reflection-based. It can be, but it doesn't have to be. Transmission and reflection both can be done. Some of the structures, they can be simultaneous transmission reflection. It's called starways, for example. These are different examples. Some of our structures that we fabricated at Coincidence Belfast. So this is a reconfigured intelligent surface. It's a transmission-based reconfigured intelligent surface. Here we have 3.6 gigahertz reflection-based surface. We did the characterization of the reconfigured intelligent surface only last week. So these are some initial results. They are encouraging, certainly, but you can see that we are scanning the beam. So we still need to look at some other things, but initial results are really, really encouraging. So we have here 4 panels, and we're using them together to have a larger aperture, like this. And we are scanning the beam electronically by tuning the elements on or off, nothing else. In this case.
So what is the difference between this and metasurface at the end?
So a reconfigured intelligent surface can be synthesized using deep subwavelength elements. It can use holographic wave synthesis. In that case, it's also a metasurface. But in wireless communications, for example, you would see a lot more referral to the reconfigured intelligent surface rather than metasurface. But actually, we are talking about the same thing.
Oh, okay.
Yes. But for example, if you use lambda over 2 sampling, so you're not talking about deep subwavelength sampling here, then it's more accurate, in my view, to call them reconfigured intelligent surface because you are now closer to an array kind of sampling, lambda over 2 limit. That will give you a very good control in the far field, but in the near field, it's not going to have the same properties that you would have from a deep subwavelength sample structure, lambda over 10 or lambda over 40. Yes.
So this is sampling greater than
It can be greater than lambda over 40, lambda over 10 that we are normally using in metasurface domain. But holographic wave synthesis approach still applies here. So holography doesn't mean that we are doing metasurface. So they can be different, but holographic metasurface means that we have a metasurface, deeply subwavelength sampled, and the way we are modulating the automatic wave is using the holographic principle that I just talked about. In our team, we do a lot of holographic beam forming and beam synthesis.
this sampling is lambda over 2?
For metasurface,
For this?
for this it can be, yes. It can be, yes. So lambda over 2, you can have lambda over 2 sampling, you can use pin diodes, etc. But you can go deeper than that. And for near field, you need to go deeper than that. Yeah. So this one here is, for example, I believe it's lambda over 2 for this example. And it doesn't matter for near field because we have specific focus on the far field application for this one. And I will very, very quickly talk about this. There's a lot of some other stuff I need to cover, and I'm conscious of time. One of the challenges of metasurfaces is that we need to bias these elements. So in this case, we're talking about the width. In metasurface, we have a lot of elements as well. We need to bias these elements. We don't have phase shifters. Remember, I talked about that. That's good. We don't have power amplifiers. We simplified all that. That's great. But we need to bias these pin diodes. That is a challenge. So we are now looking at some other techniques. Again, this works. We know how to design these kind of structures. Power consumption can be minimized using pin diodes. They're simple from that perspective. But again, if you have thousands of elements and we need to bias them, each one of them individually, they can be a challenge. So we are looking at different applications, different use cases, different technologies. This is one of them, and plasma. So the idea is that by applying an external stimulus, we are changing the phase distribution of the plasma element here, and we can use it as a tunable element. And very, very early on right now, we can tune the responses just a set of plasma tubes. We are applying different external excitations per column in this case, and then we can scan the beam by changing the phase distribution of the plasma element. The advantage of plasma is that we can externally excite the structure. It doesn't have to be dedicated biasing lines for elements we're talking about. It can be done through an external electromagnetic wave instant onto the surface, depending on its power distribution. It can be ignited at different power levels. So that's the advantage of plasma. So the first set of results are encouraging. There's something to be done here. And so we'll explore this idea going forward. But it's just to show that metasurfaces, they have their challenges as well. So we need to appreciate that. They're not the solution to everything. They have advantages, yes, but they have their own challenges as well. And biasing is certainly one of them. And we have started looking at it again, using different types of unit cells with plasma, on and off. And we have synthesized what we call electromagnetic induced transparency window, EIT. So the idea is that you can get a reflection and transmission response from this kind of structure on and off by tuning them using plasmas for different applications. So it becomes a transmission media and reflection medium, depending on the excitation level. So these things can be done using plasmas. So these results are really, really encouraging for us. What are other applications? They can be used for wireless power transfer. Again, these are different examples. We have here a near-field wireless power transfer structure setup. You can see the mathematical elements, and you can create here almost a waveguide between the end user here and the power source. And we are kind of doing this wireless power transmission through that waveguide that is generated using metamaterials. It becomes a transmission window almost. For this kind of structure, we can do focusing, and this is one of our papers. The idea was to have a metasurface here, and you can create two focal beams, and you can put the receiver 1 and receiver 2 at the focal beam, and we show that you can increase the wireless power transfer efficiency by more than 6% just by doing that. You can scan the beam dynamically, etc. These things can be done, just to give an idea of different applications. So this part of the talk, unfortunately, I have to be very, very quick, but I have another distinguished lecture talk focusing on imaging, and I will go in much more detail on this aspect of the talk. But one of the major research topics that we do in my team is computational imaging. The question that we asked, I believe, 15 years ago was, okay, they are useful for so many applications, but what else can they be useful for? Metasurfaces, hologram beamform structures, and due to our curiosity for imaging at that time, we wanted to explore that idea, and it turns out that they can be very, 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 very useful to do this kind of wave synthesis. Very quickly, I will talk about this. So the conventional way to do imaging is, this is basically the thing that we like to image, and we do what we call point-by-point scan. It's called raster scan. So the idea is that we have a transmitter, receiver, so in this case a transceiver. We illuminate the scene on a voxel or pixel by pixel basis. So you do the transmission, and you listen to the echo. You do the transmission, you listen to the echo, you do the transmission, and you listen to the echo. And then you do that for all points in your scene, and then you have the image. This is the image, this is optical domain, and this is millimeter wave domain. So QUB works fine. This is all electronically doing that. So we're doing a raster scan, but all electronically. This can be done really, really fast. This is slow because it requires a mechanical scan. The question we asked ourselves at that time was, can we eliminate this mechanical scan, because we never liked it, it's always slow for us, but also, can we keep this old electronic aspect, because it's very quick, but can we do this without using phase shifters, power amplifiers, very, very simple hardware architecture. In that case, metal surface helps us. This is how it works, or this is how it helps. It radiates these kind of patterns. They look terrible, but I will explain why they are actually very, very useful for us. So the very conventional way of doing that is we do a point-by-point scan, do the measurement, do the measurement, do the measurement for the entire scene, collect the data. That's the image that we have. Here, we are using a metal surface to radiate these kind of very chaotic patterns. They are random patterns. They don't have a main lobe to scan. The idea is to illuminate the scene using multiple voxels here, using multiple beams at a time, and then compress the measurement into a single channel, and then try to reconstruct the image using those compressed measurements. In this example, we are imaging a smiley face target. We are looking at the random projections, and we are using computational imaging techniques to recover an estimate of the smiley face target. You can see, I will go back and come back to this slide again. You can see, for the raster scan, we need to shoot every single pixel to get an image of the scene. So you can see we need to hit this mouth part, nose, eyes, and then we will get the image. Here, we already have an estimate of the scene. This is the mouth, this is the nose, these are the eyes, by using this physical layer compression approach. So we need to radiate these kind of random patterns using the holographic metal surface concept. The reference wave is the excitation that we provide to the metal surface, and the object function is these random patterns. And our goal is to be able to reduce the correlation between these patterns, because we don't want to keep receiving the same information from different masks. We don't want it to be redundant, the information. We eliminate different parts of the scene, different voxels, to reduce the correlation, and then we can reduce the number of measurements by doing that. We published a paper on that. I have some references in next slides. We have shown that we can reduce the number of measurements by more than 95% physical layer compression, as opposed to raster scan, without sacrificing image quality. So there's a big reduction. And again, this is how it works. Metal surface, different radiation patterns. We have metal elements, you can see, and each of these metal elements, they have different resonance frequencies. And we distribute them randomly. It's very, very simple. And in that case, all we need to do is we do a frequency scan. So just change the frequency, FMCW, and you change the frequency. It means that only certain subsets of these metal elements will be on. They will couple to the guided mode, and they will radiate. And because they are randomly distributed, their resonance frequencies, as you change the frequency, you're also changing the element distribution random as well. So they radiate different radiation patterns, and then you can do imaging that way. We verified the concept with so many examples over 15 years. So this is basically just 6 metal surface antennas with complementary ERC elements, TX, 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 IX, IX, IX. And we image different objects. We have even adopted these techniques from automated radar approach. With British Council, the idea worked. Again, a cavity antenna, so we did different patterns. The technique works. We have done two-level imaging. So we have here one metal surface, another metal surface. The elements, you can see that they have different resonance frequencies. So their geometrical sizes are different, and they are randomly distributed. And we scan the frequency, and we radiate these kind of patterns. We've done two-level imaging. We've done imaging of different numbers, different letters. And we are not changing here anything in terms of mechanical movement. Everything is fixed. All we are doing is one-port excitation, TX, one-port reception. We just change the frequency. That's all. K-band from 18 gigahertz to 26.5 gigahertz. So that's about 8.5 gigahertz. And we have done programmable metal surfaces. So these structures here, they're completely passive. There are no pin diodes, there are no vectors. There's nothing to bias here. It's very, very simple. Just element geometrical sizes change. That means the resonance frequency is changing. But it requires a bandwidth. You can even do frequency imaging at a single frequency. You don't need to even, in this case, do a frequency sweep, just one frequency. All we need to do in this case is we just modulate these elements on and off using pin diodes. Don't change the frequency, just pin diode on and off. We can scan this kind of, radiate this kind of patterns, random patterns, and we can do real-time imaging. So this is basically a moving platform. This is real-time image of the scene. This is the metal cup that we designed, and you can see the response of the metal cup here. And different letters of QD, we verify it with so many concepts. And we combine frequency diversity and dynamic metasurface. So we narrow down the frequency a little bit by using metasurface, but also we have the frequency diversity as well. It's a hybrid of both techniques, and we modulate, for example, this is a cavity. Inside the cavity we have a metasurface, and we modulate the metasurface using the dispersion I just talked about, and then we can relate these element patterns. We've done imaging with different targets. You can see vertical shape of the image, horizontal shape. We can do phase encoding, things like that. This is single port, in this case, excitation, single port reception device. Nothing else involved. Another fabricated example. I'm conscious of time, so I will just move on to this example I wanted to talk. And there's a recent concept that you might have heard. It's called integrated communications and sensing. In this case, integrated communications and imaging. We are using the same metasurface structure to encode both functionalities. So what we have here is this design. This is the cavity, and behind the cavity we have the metasurface. So we did these kind of random projections. And by using this cavity, we can do direction of arrival estimation in a compressive manner. We are not scanning it mechanically. We have here a source, it's a home antenna. We can estimate its location in 3D space, and then we can replace that source with an object to image, and we can do imaging of that object. So we can identify in three-dimensional space where the target is, and then once you identify the target, now you know where to communicate for communications, and then you can also do high-resolution imaging. So it's called communications and imaging combined together using the same physical layer compression architecture. And one last thing I will talk about is a very, very hot topic, and we will have some other distinguished lectures talk about this concept, analog wave computing. It's a very, very interesting idea. We will also start looking at that idea as well. As I mentioned, using metamaterials, metasurfaces, we can do a lot of things. And in this example, we are using metasurfaces to do wave computing in the analog domain. The conventional way of doing computation is we have a waveform, we do analog digital conversion, in the digital layer we do processing, and then we go to analog domain after that. So there's multiple layers involved. We are talking about high power consumption, we are talking about additional latency, etc. It turns out that we can do the calculations directly in the analog wave domain using metasurfaces. So we have different examples here. I talked about computation imaging. It becomes part of already metamaterials, metasurfaces, the computational side of the problem. So we are already in the computation domain using metasurfaces, and we can do focusing. This is essentially a lens implementation. So we're taking a Fourier transform, essentially waveform. So they are already doing, in terms of examples I talked about, wave domain calculations. And some other cool examples is, for example, we can do differentiation. So this is a paper from Andalus group, and we are doing here, for example, the edge detection. So this is an image, optical image. You can feed it to a mathematical slab in that case that is designed to do differentiation, first order, second order, and then you can do, as an example, edge detection. just by doing that. And this is from another Inglaterra's group. The idea is that these ideas can be experimentally verified. So in this example, they are showing using simple node in inversion of a matrix. So it's a 5 by 5 matrix, and you can have the inversion, so the expected and the measured outcome agrees very well. So the idea is very, very promising for the entire mathematical community, optics community, electromagnetics community. And we are, I think, making a very good progress on that. And it's going to have a huge advantage in terms of how we do computations. It's going to change the way we do computations going forward. So just to conclude my talk, I talked about different application examples of metasurfaces and metamaterials, and they can do so many things. I think the main takeaway from this talk is that we are not looking at these structures as pure antennas in the far field, but as an enabling technology, they can do so many other things in both far field and near field domains. And some applications are shown here are certainly good examples of what they can do. And I also shown these ideas most up to W-band frequencies, K-band, W-band, but obviously they can be scanned to other frequencies, including optics as well. And there is a huge literature in different applications covering those frequencies. With that, I would like to thank all of you, and I'd like to conclude my presentation. Thank you.
Thank you very much for your interesting presentation, and now we are open for questions. So I can start with a question. I have seen that you are using a scan using different frequencies.
Yes.
Well, in this case, it is important to the fact that the imaging can be different at different frequency. I mean, so I don't know the impact of this part and which are the applications. Here we have also students that are on bachelor, so for them perhaps it is easier to understand the applications because perhaps it's a little bit difficult for them. So also focus on the application of that.
So, Christian, this is a very, very good question. Thanks so much. So this is a very, very, very point. If we are requiring bandwidth, we need to make the assumption that we are operating across a reasonable bandwidth that the object response doesn't change that much. So for the K-band example, for example, I talked about here, the reflection response of the object is almost the same. It doesn't change that much. But if we are, for example, doing as an extreme example, let's say the X band, and then we are jumping to terahertz band. Then we are talking about two different, very different applications, frequency spectra there. Then we need to look into the different response of the object, then do the inversion. So for the frequency bands that we're operating, the object response is fairly stable. Application-wise, the biggest application for us is if we have an object that we cannot see in optical domain. And what I mean by that is, if we have a scenario, for example, we are right now in a very beautiful classroom, I can see each of you in optical domain, there's no problem with that. I probably don't need microwave or electromagnetic, this kind of low frequency imaging systems to be able to see who's here, because I can see all of you. But for example, let's say airport scanning systems. You might have seen those big scanners. For security screening, I might be carrying, let's say, a gun phantom, right? It's hidden behind my clothing, and I have, in that case, an optical camera, and I cannot see what is behind, obviously, this kind of clothing. So in that case, we need to be able to look at the same scene at a different frequency, because at optical frequency, thankfully, our clothes are not see-through, right? So that's good. But also, from that point of view, we cannot reveal what is behind underclothes for that particular example. So to be able to see that, the threat object example I talked about, a metal under the clothing can appear very, very clearly at a different frequency. For example, I might have an object hidden under this desk. So I have, for example, I might be having an object behind the desk, under the desk. I'm looking at the desk, and I cannot see what is under the desk. Optically, it's opaque. So the same desk will be transparent for me if I go to a different frequency spectrum. At microwave, I will be able to go through that material, and I'll be able to interact with the object behind that desk. So it really depends. That's a very, very good point. So if you have already a good line of sight and then optically everything works, great. If you're doing remote sensing, for example, in space through clouds, optically, the ground is not visible because the ground is blocked by the clouds. But then you go to a different part of the electromagnetic spectrum and it becomes transparent. You see what's invisible. And I have a talk actually, one of my talks is seeing invisible. So to see invisible at optical wavelengths, for example, we do micro imaging.
Okay, thank you. I think it is very clear, and it is beautiful to see that now they want to see the invisible, and the next paper will be on the invisibility, but we will see later then. And now, okay, I think for students perhaps can be also surprising to understand that with antennas you can do an image of that. And this is a very clever way to obtain an imaging by simplifying the system, because you have just something that is not active and the change of frequency. Yes. So I think it's very. Do you need artificial intelligence to reconstruct the?
So we can. So at the very beginning of my presentation, I talked about a generic set of pictures. So it's this slide here, and this part of my imaging talk as well. So here, just very, very to show this here. And we don't need artificial intelligence, but we can use artificial intelligence. So here we have a K-band imaging system. It produces a low resolution image. To get a super resolution image, we can either go to higher frequency, that's one option, but if we cannot do that, if it's not an available option to us, we can then use a deep learning model, and then we can drastically improve the resolution of the system. So here we are looking at low resolution. This is high resolution, and physical point of view, hardware-wise, we are not changing anything in the system. We take the input, we get the image, we feed it to our deep learning network, and we get the super resolution image from that. So we can use that, yes. We can do object classification. It's one of the popular examples for security screening. We can say it's a phantom, suicide rates, whatever it may be, or it can be super resolution to improve the resolution. It can be deep blurring. So for example, when we are doing imaging, when somebody moves, the image gets a bit blurred. So we can de-blur that image and get a better, much clearer looking image using deep learning frameworks.
Okay, thank you very much. Some other questions from the audience? Okay, if it is not the case, let's thanks again. And we can go to the next speech. The next speech is from Özlem Özgün. I hope the pronunciation is acceptable at least. And the title is A Magic World of Transformational Electromagnetic, Invisibility and Beyond. So here we have the problem, the contrary of the problem we have seen before. So Dr. Özlem is currently a full professor in the Department of Electrical and Electronics Engineering and Vice Dean of the Faculty of Engineering in Hacettepe University, Ankara, Turkey. Her research interests includes various topics in computational electromagnetics and radio wave propagation, including electromagnetic radiation and scattering, numerical methods, domain decomposition methods, transformation electromagnetics, stochastic electromagnetic problems, and optimization techniques. Dr. Özgün is a senior member of IEEE and URSI and was a past chair of the URSI Turkey Steering Committee. So, welcome Dr. Özlem, and stage is yours.
Thank you very much. So, by the way, I think, can you hear me? So, it's okay right now? Okay. So first of all, thank you for coming here and organizing this excellent session, workshop. I'm so happy to be here. This is my first time in Perugia. Not first in Italy, but first time in Perugia. So I'm quite impressed by the history and the nature of this beautiful city. So I'm from Hacettepe University, which is one of the leading universities in Turkey. My major area, research area, is computational electromagnetics, radio wave propagation, in principle development of some numerical techniques for electromagnetic problems, as well as the transformation electromagnetics. So before starting this topic, I'd like to emphasize that this concept is also known as transformation optics. So if you are in the optical regime, of course you can call it transformation optics, but if you talk about electromagnetic waves, microwave regime, then it may be called as transformation electromagnetics, okay? So I prefer to use transformation electromagnetics since I'm an electromagnetic engineer. Okay, so first of all, if you know this university, Hacettepe University, so it's a huge public university in Ankara, which is the capital city of Turkey. So we have two main campuses. So I'm located in Beytepe campus in here, our department here. So medical school is located in the campus. It's a huge university. Okay, so before actually the concept of transformation electromagnetics, I would like to start with asking this question. So how do we see the objects in general? Okay, so actually you know the answer probably. So we see the objects because the light is scattered from the objects and you can see them, right? So the concept of scattering includes some different wave phenomenon like diffraction, reflection, refraction. Okay, so we have different wave mechanisms so that we can see the objects. So if, for example, in engineering context, so this may be the antenna, for example, radar antenna, and you may try to see the, for example, the target aircraft using your antenna. You can track this one, right, by detecting the scattered fields from the object. But now, assume that you want to make this object invisible somehow. Okay, but this invisibility is, of course, the perceptual invisibility. So the object is over there, but somehow you don't see the object. So if you notice that, so can you see the background? So this background image shows the plane wave spectrum, the plane wave distribution. So for example, in the first page, you see that plane wave comes to the object, but due to the scattered fields, so the wave pattern changes because of the diffracted or scattered fields. But now, assume that we have an object here, and somehow we code this object by a transformation medium or metamaterial medium, in other words, so that the waves are bent and go in this, for example, in this path, for example, so that any observer at the outside region doesn't see this object because there are no scattered waves coming from this object. Okay, so somehow you can guide the waves so that there is nothing here. Sorry. Okay. So one well-known example, actually, the Einstein's theory of general relativity. So in principle, gravity is the bending of space and time due to the massive objects, right? Therefore, for example, if there is no any massive object like sun, for example, the light may go in the straight path, but whenever you put a massive object, so this object bends the space and time, you see this bending in the picture. So the light does not go in the straight path, maybe curved, and this object may appear in the other place. Okay, so this is another picture for the same thing. So this is like you have a sheet, you stretch sheet, and you put a ball, and this ball creates a black hole actually in space. Okay, so another interesting example is the concept of mirage. Also, another one is ducting phenomenon. This is a very popular and undesired effect in propagation problems. So you know mirage, for example, you are in a desert and you see a water, but this water is is not there, right? Why? Because actually there is water somewhere else, but you see the water here due to the bending of the light. So also the ducting ducting is also similar. So ducting is due to the Snell's law of refraction. So if there is a medium having different refractivities, then the wave bends from the layers, and then actually it may, for example, go like this and then bend from the surface. So this will be guided through the ground like a waveguide. Okay. So that you don't see the object in the original place, but rather than in another place. So this is a picture, the real picture, showing the mirage concept or ducting concept seen at the Francisco. There is an island here. You see this island, but the island is not there, somewhere else. Okay, due to the bending of the light. Okay, therefore we can control, if we have any means or tool to control the electromagnetic waves, so we are happy actually. In the previous examples, you don't have any tool to control the waves. Okay, so for example, mirage or ducting are over there due to the atmospheric conditions. But the concept of transformation electromagnetics or optics is a very actual nice technique, which is also used in invisibility and in other applications, as Professor Okan mentioned. So this is based on the form invariance of Maxwell's equations. So the basic idea is that, for example, suppose we have such a simple space, original space with ordinary coordinates, and the medium is, for example, a simple medium like a free space. Okay, and notice that the wave goes in this direction, and assume that you want to change the path of the wave, let's say light, in this manner. So one method, actually, what you can do is that you can, for example, distort the space so that the wave is going like this due to the coordinate transformation. Notice that this is R tilde shows the distorted space due to the coordinate transformation. But the medium is still the same, simple medium. And this concept tells you that we can actually replace we can realize this action by constructing an equivalent model such that the medium becomes an original space, still original space, but the medium is replaced by an anisotropic medium, epsilon and mu. They are dyadic, inhomogeneous, anisotropic, and very complex medium. Okay, so you achieve the same action actually. Also, this concept actually is not new, can be traced back to the beginning of 19th century, but this was almost mathematical. But after 2000 and almost 2006, after Pendere's work, so this concept was used in different applications. So this is just the mathematics, simple mathematics to get the idea. Notice that these are the Maxwell's equations, two curved Maxwell's equations. So we have, remember from electromagnetic courses, so we have epsilon mu parameters, permittivity and permeability. And in the distorted space, we have the same medium, but the coordinates are replaced by the distorted or transformed coordinates. T refers to the coordinate transformation. But of course, the main issue is how to define the coordinate transformation. This is the major issue. But on the right part, you see the anisotropic medium. Notice that epsilon mu, these are dyadic, reflecting the same action actually in the original space without any coordinate transformation. Okay, therefore you can design very exotic and very interesting materials using transformation electromagnetics or optics. Okay, so don't worry about this mathematics, but it tells us the main idea such that this epsilon and mu are defined by the Jacobian of the transformation. So this is the Jacobian matrix. Notice that these tildes are the transformed coordinates, the others x, y, z, these are the original coordinates. Somehow you define a coordinate transformation, you put them into the Jacobian matrix, and then you can define the material parameters. Okay. So this is the whole thing, actually, main idea in transformation electromagnetics. Somehow you define your coordinate transformation according to your purpose or design parameters, and you use the form invariance of Maxwell's equations. You replace this action, coordinate transformation action, by a metamaterial. So, but the realization of this metamaterial is also another issue, okay? But in principle, in transformation optics, it is quite, most cases, it is quite difficult to realize such material because the medium becomes an inhomogeneous, right? It depends on coordinates. So it is quite difficult to realize these materials. So scientists, researchers usually use equivalent medium concept to realize such exotic materials. Okay, so by the way, I'm not a practitioner. Okay, so I will later on I will show you how we can make use of these materials in computational EM. This is also an interesting, I think. Okay, so this is the concept of metamaterials. So I will not go into the details because Professor Okan mentioned about this concept. But I like this picture showing the analogy between a natural material and metamaterial. So the key word is basically the control of electromagnetic fields. So as if the natural atoms change the behavior of light passing through this medium, so meta atoms put in a periodic structure maybe, right? So and creates an equivalent or effective medium such that you can change the behavior of light or electromagnetic waves in a desired manner. Okay. So also negative refraction concept is quite interesting, and actually this may be the first topic in the context of metamaterials, because natural materials, epsilon and mu parameters have to be positive. But if you, for example, design such an exotic material such that permittivity is negative, then you can change the course of electromagnetic wave. Like this is like magic, but not magic actually. This is not a science fiction, but you can do this actually. So this is the concept of negative refraction. For example, think about the Snell's law. So in, for example, double positive system or material where epsilon and mu are both positive, then you see such a refraction due to Snell's law. But if the material is has negative permittivity or permeability, double negative region, so this is actually bent in the opposite direction. So here you see this idea. So if you just look at the wave behavior inside the slab, so you see as if the wave is going in the opposite direction. But this is just the direction of the wave. This is the k wave vector. But the power propagation is in the forward direction. Okay, it's an interesting phenomenon actually, showing the negative refraction. Also, another well-known and famous application in those years, proposed by Pendry. So negative refraction makes a perfect lens applications. So, for example, just putting a mathematical region whose refractive index is negative, for example, -1, you can get the perfect image of this, for example, point source. So here you see the animation. So we have two dots here, and we have a metamaterial layer in the middle part. So the source is propagating, and at some time you'll see the perfect image of this source here. Okay, so you can do this by metamaterial layer. After that, in 2006, Pendry and other scientists proposed the concept of invisibility cloak. So the idea is, as you see here, just concentrate on this picture, for example. Suppose that we have an object here, circular object, or this may be a circular region where you can put anything inside this region. Then this is the source, for example, your eye or antenna. And for example, this is the ray optics interpretation of the electromagnetic waves going like this. Okay? If this were nothing here, then you would see this light propagating in the straight direction, right? But whenever you put an object here, you create a contrast somehow, whose material parameter is different from the free space. then obviously you will see scattered fields from the object. But in the invisibility cloak, you code this region by a blue metamaterial region. This is the cloaking region, such that the waves are bent, for example, and goes like this, so that you have still wave or light propagation as if it is propagating in free space. Okay. For example, if you put an observer here, then this observer doesn't see this object because the scattered field is like as if it's coming from nothing, right? So this is based on the coordinate transformation. You see how we apply the coordinate transformation approach. So what is the idea in coordinate transformation? This is the major point. So the coordinate transformation actually transforms all points actually in between R1 and R2, so this layer, transformation layer, to the whole region between the origin and the outer circle, actually 0 and R2. So what coordinate transformation does is that all coordinates inside the transformation medium are transformed to the whole space occupying the circular region with radius R2. Another saying that the circular region is transformed to a point. So point meaning this is invisible. Okay. So therefore you change the shape of the region actually. You transform the circular region to a point which makes it invisible. Okay. But as I said before, so notice that the transformation medium is quite difficult to realize because, for example, even in a simple case, this is again from this study, even in the simple case, the material parameters are functions of R. R is the distance. If this is a circular cylindrical region, R is the distance from the origin. Okay. Therefore, it is quite difficult to realize the perfect materials. But in this study, they used reduced media by making some approximations. So this is the experimental cloak actually proposed by this study. Okay, so this is the actual experimental setup. So you see that, so this is the object without cloak. Notice that the plane wave is coming, but you see the shadow region actually on the other side of this object, right? Also you see the diffracted scattered fields. This must be running, but anyway. So this is the theoretical cloak. So notice that we have this plane wave distribution hitting to the object. So you see the strange wave behavior inside the cloak, and then the same, plane wave is going like this. So as if there is nothing here. So this is the cloak with the reduced media after some approximations. Okay, and then just after the cloaking approach in 2007, we proposed the concept of electromagnetic reshaping. So this is the generalization of the invisibility cloak such that actually rather than transforming the object to a point, just transform the object to another object of different shape. For example, so this is, for example, circular object just caught by a exotic material transformation medium, metamaterial. Then this observer sees like this object like a square object. Okay, this is again due to the coordinate transformation. So, okay, so actually here is the, again, don't worry about this one, but you see that there is a coordinate transformation. You just move or map some coordinates to a new coordinate somehow, right? So, for example, this the square object coated by this yellow transformation medium, and you map all the points inside this yellow region to the region between the circular one and the outer dashed boundary, which means that yellow region is mapped to the region blue plus yellow, such that the circular one is seen as a circular one. So invisibility cloak is a special case if, for example, Rn becomes 0 here in this transformation, which means that this square region is mapped to a point which makes this square object invisible. Okay, so you can control somehow the behavior of electromagnetic waves or light. This is just a simple simulation for proof of concept. We reshape a circular scatter as a rectangular scatter, which means that you see the original problem, which means that we have a real cylindrical object whose cross-section is rectangle. So this is the source. You see again, for example, the shadow region on the other side and distortion due to the scattered fields. So here we have a circular object coated by a transformation medium, and the main action of this transformation medium is to make the circular object similar to the square object. Okay. This is a movie, another simple simulation. So we have such a, for example, object. So why we put such an object? Because when we make the curve, so we can reduce the radar cross section. So this idea may be used for that purpose as well. So rather than dealing with, for example, if you have a square object and coated by transformation medium, and square object is seen like this new object with curved surfaces. Okay, so I think you see this strange wave behavior just on the corner due to this coordinate transformation. And then in again 2007, we applied this method to waveguides, reshaping and miniaturization purposes. So for example, this shows you that if, for example, circular waveguide is filled with such an anisotropic metamaterial region, so this becomes equivalent to such a rectangular. Okay. For example, if you have such space restrictions in certain problems, applications, and you can reduce the space by replacing the square one with circular one and filling the object by an exotic material. But of course, the design of or realization of this material becomes difficult. Okay, so here you see how we apply this transformation. So on the left side, you see this, reshaping. So we have this original waveguide, square waveguide. So this is the equivalent waveguide filled with metamaterial regions. So notice that we can change the coordinates and design the material parameters based on this transformation. Another one, miniaturization of parallel plate waveguide. So for example, if we decrease the thickness of the waveguide, then you know that the operation frequency must be larger than the cutoff frequency of the waveguide. Then as D decreases, cutoff frequency increases, then in principle, electromagnetic waves cannot penetrate or cannot propagate through this medium. Okay? But when you propose such a transformation and put some, transformation medium here, then you can achieve propagation through the miniaturized part of the waveguide. Okay, I will show you just quick simulation examples. So, for example, this is reshaping a square waveguide as a circular waveguide. So you see the wave pattern occurring in this circular waveguide filled with isotropic transformation medium. This is like transforming these, curved, like squeezing and enlarging, etc. Okay. We also compared them with the analytical and results for different modes of the waveguide. This is another simulation example. So, for example, if we have a parallel plate waveguide dominant mode is propagating, and for example, if you miniaturize the waveguide like this without putting anything here, then you see that the wave cannot propagate through this medium. Okay, so since the operation frequency is less than the cutoff frequency of that region. But if you design a coordinate transformation, put some transformation medium here, notice that this is like squeezing this wave pattern inside this region. So this is possible by coordinate transformation. So I said that the realization of the materials may be difficult due to the spatial varying nature of the material parameters, but we have seen that for certain cases, the medium becomes very simple to realize. For example, let's say if you have big waveguide and we can reduce the thickness along y direction, then it is enough to apply the coordinate transformation only in the y direction, and the medium becomes uniaxial medium. If we have, for example, transformation in both directions, like A, B, in xy directions, so the medium becomes biaxial medium. Or you can also use the cylindrical coordinates, and the material parameters may be simpler to realize. Okay, so these are again some pictures for the field pattern, TM11, TM21 modes for the different miniaturizations in y direction or in xy directions. Okay, also the transformation electromagnetics or optics has a quite rich literature. So scientists developed some concentrators, rotators, focusing, etc. Okay, so in this talk I'll of course present my own contributions and own perspectives. So later on, after these studies, we thought that can we use this concept to eliminate some difficulties in computational electromagnetics. So what's the computational electromagnetics? So you develop some numerical models, codes to understand the behavior of electromagnetic waves, right? So actually, the concept of coordinate transformation is not new, and it was used in the concept of perfectly meshed layer. So, so what's perfectly meshed layer? So there are different, methods to realize the PML method, but one major one is the complex coordinate transformation, meaning you actually transform again the coordinates inside this PML region. PML meaning if we for example, you realize that, let's say, scattering problem, you have an object here, and you illuminate by a plane wave, and you try to calculate scattered fields, right? So you have to put this object into a closed box, and you have to apply some artificial absorbers around this object to eliminate the wave reflections. So this is like an absorbing material. So if you replace the coordinates by the complex coordinates, by using some decaying function, then you achieve the same thing. So actually, this is again due to the form invariance of Maxwell's equations. There's a one-to-one correspondence between the coordinate transformation and the material parameters. You can design a material actually for the absorption inside this region. Okay. But after 2006, after cloaking approach and reshaping approach, we thought that we can actually make use of these exotic materials to overcome some difficulties in multi-scale problems. So multi-scale meaning if we have a problem including different objects, different sizes, like for example, we may have some big objects, or we may have some thin objects, very small sources, for example, radiating sources. In order to use a full wave method like method of moments, finite element method, finite difference time domain method. So you have to refine the mesh around such thin objects. Notice that you have very fine mesh, which increases the number of unknowns, also which increases the ill conditioning of the matrix equation. Okay. So the idea was that rather than dealing with the original one, just remove this part, and then the white part is removed, and we can coat this region by a transformation medium. So this will be equivalent to the original one, and we can recover the near field after the transformation. Okay, so this was so that we can eliminate the mesh refinement, easy meshing, uniform mesh, less unknowns, and well-conditioned matrix. So we called them as software metamaterials actually after this study. So here you see the original problem. For example, these are again simple ones. So we have very small, tiny sources here, and you want to use full wave method, so let's say finite element method. Notice that you have to introduce many unknowns around this object like this. But rather than using this one, just remove this part and then coat this part by a transformation medium. So the transformation medium can be designed separately for each source, or maybe designed as a whole. We tried many different techniques to see how we can achieve this. So here you see the transformation, and as I said before, the near field is recoverable after the transformation. So the main advantage is that you don't have to deal with the mesh refinement and difficulties, and you can use uniform mesh. These are again some simple benchmark simulation examples. So this is the original problem. Original problem meaning that you, by force, you design a mesh refinement and then use the finite element methods. Okay, and then the other one, equivalent problem, meaning that you design a transformation medium for each source and you get the same action. Okay, notice that in the outer region everything is identical, actually almost identical with the original one. Also, you reduce the computational load because you don't have to deal with much more unknowns. Okay, so this is also another one, original problem and equivalent problem. So notice that we have such a strange, let's say, like a blanket one, and you just compress this region, this field distribution into this region along such a coordinate transformation. Another one is the spatial domain compression. So the idea was actually, for example, suppose we have such a, can you see that, I don't know what, suppose we have such an L-shaped object. This may be a paraboloid, for example, huge reflector antenna. Then in order to use a full wave method to simulate this problem, you have to put the whole object into a box, for example, a rectangular one, or at least such a trapezoidal region denoting the convex hull of the object. Okay, so if you put such a region, then you have to introduce many unknowns in this region. Okay, you have to occupy this region to simulate this problem. But rather than just, this is just a convex hull. This is the standard rectangular one. It's the convex hull. But rather than dealing with the inner huge part, white region, then introduce a metamaterial or transformation medium such that this whole field information is squeezed, compressed into this region. Okay, so there are, of course, some questions regarding those applications. One major question is that should we use fine mesh, very fine mesh inside the transformation medium? So not in principle. So we compared the error for different thicknesses and different cell sizes. But the main reason is that when you, this is the ray optics interpretation of the domain compression. So when you apply a coordinate transformation, for example, like in this direction, then notice that the path becomes longer compared to this one, the original one. Okay, so therefore the actual light or electromagnetic wave must move faster actually in this long path. So since frequency is fixed, wavelength actually decreases. So that actually you don't have to use fine mesh. The mesh resolution will be enough to capture the field behavior in those regions. So here you see different, this is a wide angle, narrow angle ones. So you see how the fields are squeezed into this region for compressing the fields. Later on, we thought that actually we can use a similar idea for some stochastic methods, like rough surface scattering problems. So are you familiar with Monte Carlo simulations? For example, if you have a, nothing is actually deterministic in nature. Everything is stochastic, probabilistic, right? So for example, you are in radar application, and this may be a sea surface. So, and you have a radar antenna, okay, trying to detect the target on the surface of sea. But once you simulate this one, every time the surface of the sea changes, of course, you will get different fields from the target, right? Therefore, you have to use the statistical methods like Monte Carlo simulation, which means that you create the surface many times, let's say 50 times, 100 times, then you run the problem again and again and take the average, for example, to get the average behavior of this phenomenon. This is rough surface scattering. But the main issue is that if you use a full wave solver, again, you have to change the mesh again and again for each surface to make this analysis. So we thought that, so we don't have to do this actually. You don't have to change the mesh. So just put the transformation medium like this. Notice that gray and the blue one refers to the computational domain where you create a mesh and then solve it. So this white part is the empty one. And then this, just move the coordinates inside this blue one into the region occupying the blue plus white, so that the transformation medium mimics actually the behavior occurring in blue plus white region. Okay, again due to the coordinate transformation. So you see that again ray optics interpretation of this coordinate transformation. So you achieve the same response actually in the equivalent problem. Later on, we applied this method to objects with rough surfaces. We also use perturbation methods. Actually, if the surface roughness is very small, we incorporate it into the transformation medium in another study. So here you see this original problem with, for example, fine mesh. But here you have a flat circle where transformation medium is used as a coating. You get the same response, actually almost the same response. Later on, we applied this to waveguides with rough surfaces. Similarly, we may have, at especially higher frequencies, of course, the surfaces are not flat and we produce some roughness. Again, we put such a transformation medium, and everything is occurring actually in this transformation medium, so such changes. Also, we applied this to ridge waveguides. For example, the position of the ridge may be random, but you don't have to change the mesh. You just only change the material parameters to, for example, simulate this problem according to this transformation. Okay. Also, later on, we applied this technique to arrays or randomly positioned objects. So there are some applications requiring, for example, sparse arrays, where, for example, if you have array antenna, let's say, and where the positions are random, okay? In order to simulate this technique using full wave solvers, again, you have to change the mesh again and again, okay? Notice that here we have a single transformation medium, and all points in this medium are transformed to the whole region occupying also the white region. Okay, so here again, the simulation example. So this is the original one with fine mesh. And we now in the equivalent problem, we have a white region, empty region actually, but we have a transformation medium here. All points or coordinates are transformed. And this one, actually, this is the recovery of the field information from this equivalent one. So we expect that this top and bottom ones must be equivalent. Of course, there are, there may be some numerical inequities, errors. Okay, so this is another example, arrays and randomly positioned objects. In that example, we have a separate transformation media. So we also tried a strange transformation. So this is, for example, suppose that we have again a sparse or randomly positioned arrays whose separation may be different. Okay, rather than dealing with such a mesh or computational domain, we have such a uniform mesh, and we only change the material, for example, in this region according to the difference between this object. So this is many, translations or squeezing operations are applied in such a problem. Okay, so this is also the same concept. So this is the generated real mesh with uniform simple mesh, and then we just transform. This is a virtual mesh after the transformation, but we don't deal with this one, of course. We only deal with the generated mesh, but the transformation medium does this job actually, the transformed mesh. Okay, later on, I will finish in, I think, 5 minutes. later on in Cartesian grid, we applied this idea to eliminate the staircasing error in finite difference time domain applications. If you are familiar with the finite difference time domain applications, you have to use a simple grid structure to make the simulations. You don't use any triangles, etc., irregular shapes. But once you have a curved object like this, then you experience such a staircasing error, right? Why? Because the mesh doesn't fit to the curved surface. So to eliminate this problem, so we have, for example, such a circular object. We don't have to deal with the geometry. Just use a Cartesian grid, put a transformation medium, and then make a transformation again using this coordinate transformation such that you eliminate the staircasing error. So on the lower part, so this is the original problem, meaning that we have a square object. Square object fits to the rectangular grid, of course. There is no staircasing error here in the original problem. But once you tilt the object like this, then this diamond-shaped object doesn't fit to the grid. So you experience some staircasing errors. But in order to eliminate those staircasing errors, just put a transformation medium here, make this coordinate transformation, then you improve the accuracy. So here you see the improvement actually. The red one is the original problem without staircasing error. So on the left part, the first one, rotated original problem diamond with staircasing error, blue one, and the black one is the equivalent problem with the metamaterial or transformation medium. Okay, and also we applied this technique for inverse scattering problems, for optimization problems, because in optimization problems as well, you have to run the full wave solver again and again, and you have to make the mesh generation to solve such problems in optimization problems. So rather than dealing with the mesh generation in each case, you just put a transformation medium, like dark gray regions show you the transformation medium. Then you make such simple coordinate transformations, right? Then actually you can improve the accuracy. Also, you decrease the computational load. It's just using a single mesh and changing the material parameters. And finally, we applied this method for microwave imaging, a more realistic problem, so breast cancer detection problem. So notice that the main action of the coordinate transformation is that, so just use a simple grid and don't have to deal with the geometry. Just put some transformation medium to mimic the behavior of this or mimic the action of this geometry. So again, we apply a genetic algorithm. We applied genetic algorithm here. So we optimize those points reflecting the spline approximation of this breast cancer tumor, actually in this tissue. Okay, so that's all for my talk. So this is just a funny conclusion, is that this is a cross-eye illusion, not hologram, but cross-eye illusion is that. So you can, for example, make this cat disappear meaning invisible, by using an invisibility cloak. But actually, if you take the inverse of the invisibility cloak, inverse transformation, you can make this cat into existence actually. So just again use a transformation layer here, so this cat is seen at a different location due to the coordinate transformation. Okay. Thank you very much for your attention.
Thank you very much. Thank you very much for your very interesting presentation. And there are questions from the audience. I start with a question then. Of course, probably you that work on invisibility receive a lot of questions on invisibility and the cloaks of Harry Potter, I think. This is also
But
why you call it cloak, because to recall something magic or something like that, because you can obtain the invisibility. So my question is, how close we are to this beautiful effect of covering something and make it disappear. I mean, for example, we have seen a simulation in which the object immersed in a field is quite invisible because it doesn't change the electromagnetic wave. This is something that happens only on a single frequency, or we are able to obtain in a larger spectrum in order to have the invisibility not only for one color but for one frequency? Or so this is the first question.
okay, yeah. Actually, those all simulations are in a single frequency. Even in FTDT simulation, actually, we have a narrow bandwidth actually. So of course you are right. So the frequency is an issue. The bandwidth of frequency is an issue. But for realistic design of cloaking, so I'm quite away from this this one because I believe that this is difficult. Although there are some efforts, so some esteemed researchers are working in this regard. But I think it is difficult because of the spatial varying nature of this, coordinates. So it's very difficult, I think. You may use an equivalent medium approach to simplify this, design using some splittering resonators, etc. But I believe that we are not very close to.
Oh.
But maybe other researchers do think in a different way. Yeah.
Of course, but I think there are still applications. For example, in to be invisible to radar. Do you know if there are already applications on that, and if they are using stealth technology? I don't know, for example.
Yeah. So actually there are, stealth technology that covers different techniques. So people use some, reshaping the titles or painting maybe. But there are also some, surface type structures to make them invisible, frequency selective source or meta surfaces. So actually, I think it may be possible if, especially meta surfaces are quite interesting. I think you can control many things, especially design on the radome of the aircraft. So you can make it invisible. I think. Yeah, maybe in the future we will see much more interesting applications.
Of course, the research is on this purpose. So.
Yeah.
We do research in order to obtain results in the future. No, I think one of the challenges to also obtain this invisibility at different frequency, and I think this is very difficult. Because, okay, other questions? Okay, if it is not the case, let's thanks again for his presentation, Ozian, sorry, and we can go to the last presentation for this morning session. I would like to recall all of you that we have the lunch break, and we prepared lunch here for all the audience also. So it is an occasion also, if you are shy, to ask questions here. When we are there in front of the food, you can ask if you have some curiosity, and this is a good occasion also for networking. So I hope you will join, all of you will join to the buffet lunch. Well, so as I said, this is the last presentation for this morning session. Then we have other two presentations in the evening. And the next presentation is from Pei-Yen Chen. The title is Non-Hermitian Electromagnetics and Its Application. Professor Pei-Yen Chen is from University of Illinois, Chicago, USA. And he is on the Department of Electrical and Computer Engineering And his research area spans a wide range of electromagnetic spectrum, including applied electromagnetics, RF antennas and circuits, wireless sensors, metamaterials, nanophotonics, and quantum optics. And he is a fellow of IEEE and optical OSA. Okay, so floor is yours. Thank you.
Thank you very much, Cristiano, for your kind introduction. First of all, I would like to thank Professor Lement for inviting me to join this distinguished lecture series. Cristiano just gave a microwave distinguished lecture at UIC a couple of months ago, and I didn't expect I would visit Perugia shortly. Okay, good afternoon, everyone. Buonasera. And my group at the University of Illinois Chicago mainly focuses on EM, electromagnetics, metamaterials, antenna, and circuits. But metamaterial is always my favorite. But I don't want to talk about metamaterial this morning. We'll have too much metamaterials in one day. So today I choose a different topic, non-emission electromagnetics. So we just started this research maybe 6 years ago. And in the past, I also worked a lot on photonics and also wireless sensor and system and the design of the circuits and antennas for IoT sensors. So this topic was inspired by my very good friend and collaborator, Rami Elganaini and Sahim Ostamish. It's about non-emission quantum mechanics. It's a very hot topic in quantum. It was initiated only 20, 30 years ago. And when we study quantum mechanics in undergraduate, we know if we have a non-emission Hamiltonian, it cannot have a real eigenvalue. But Carl Bender, he found an exception. So if the quantum non-emission Hamiltonian, it follows PT symmetry or parity time reversal symmetry. Even the Hamiltonian's non-emission, it can have a real eigenvalues. And let me see how it works. So parity operator means space emergent. S becomes minus X. Momentum P becomes minus P. Time reversal means T becomes minus T. Or if you look at the phasor expression, exponential I omega T becomes exponential minus I omega T. Just take complex conjugates to the phasor term. So, but to make this happen, we need a complex potential. Of course, this is debatable. It's not, it may not be possible right now on Earth. But if we can make this happen, then there's a very interesting behavior. So this is the eigenstate or eigen energy in quantum, and epsilon is a non-hermiticity in this potential term. If I sweep epsilon in the potential, you see there's an exceptional point. It divides the system into a PD symmetry and a PT broken phase. So in the PD symmetric phase, we have a real eigenvalues. And more interesting, there's an exceptional point that the eigenvalue collapse, and then it experiences a bifurcation effect. So I like to study this by exceptional point and its real-world application in electromagnetics. So if we look at the Schrödinger equation, we look at the wave function, we look at the potential and Hamiltonian. But if we look at the periaxial wave equation, when we study laser, we study the basal beam, they share some similarity. Schrödinger equation and the Maxwellian system. So instead of looking at the wave function, we look at the E field. Instead of looking at potential, we look at the refractive index. So of course, it's not possible to have complex conjugate pair, complex conjugate potential, because potential cannot be imaginary. But it's possible to have a complex conjugate refractive index. So it means one material is gained, the other material is lost. And it was published, was first demonstrated by Christodoulides and Rami Elganaini in 2008. So, so basically, we need to pair a gain and loss median. So if I apply parity operation, space emergent, I just rotate their position. And then if I apply the time reversal operation, T operator, so loss becomes gain, gain becomes loss. Why? Because if we look at the power, in the loss median, energy decays over time, but in the gain median, energy grows over time. So they follow a time reversal relationship. So if I have a combined PET operation, space emergent, time reversal operation, the system becomes identical system, remains unchanged. So it was demonstrated by some group in Europe, Reuters, I think it's in EPF et al. They demonstrate if I have a two-wave guide, one with gain, the other with loss, of course, direct wave guide, and I pair, they are coupled. It's kind of like crosstalk, and then I can make a PT system. So this is a profile of refractive index. The real parts are the same, and the imaginary parts of refractive index, they are the same in magnitude, but they have different sign, positive and negative. So one is gain, the other is loss. So and then they study the eigen mode of the waveguide system versus the gain loss parameters. You can control doping or defect, right? Dopes erbium to have gain. Then they observe exceptional points. And so around this exceptional points, eigen mode splits from 1 into 2, and with a very, very sharp slope. And I want to use this slope for several applications. I'll talk about this later. This is a bifurcation effect around the exceptional point. It divides the system into the PD symmetry and the PD broken phase. And this is a review article written by Professor Andrea Lu, and there are these several applications. Like we have long reciprocity, nonlinearity, we can study the topology, we can study the engineering of band structure around exceptional point, or we can have some circulating movement around this exceptional point, some topological phase. Okay, so I'll just focus on this PD symmetry in microwave, RF and microwave, rather than optics. And so it also gives us this non-Hermitian system also gives us many new design degrees of freedom in EM. So in the world of metamaterial, so we have this 2D design space. So we have a positive and negative permeability. Let's say dielectric materials in phase 1, and we have some negative permeability metamaterial MNZ, or we have some double negative metamaterials made of ring and wire median, and we have plasmonic materials, and it has a negative permittivity. But if we introduce non-Hermitian gain and loss, we also look at the imaginary part. So we have a three-dimensional design space. Just gain and we look at the real part, both real part and imaginary parts of the materials properties. And so this is a very exciting research areas, new research areas. So if I look at the one-dimensional PT symmetric systems, it's very simple. So one-dimensional, it's just a scaling problem. So it's two-port network. I have a passive median, I have a gain median, and I flip the sign of the imaginary parts of permittivity, right? And I know if the median is very, very thin, then I can model this guy with impedance surface, right? So if T is sub-wavelength, then I can model this guy with impedance surface, or more specifically, positive surface resistance and negative surface resistance, plus some parasitic capacitance. Okay, and this guy is exactly like a beta surface, surface impedance. And then they are separated by a short section of transmission line. So in RF and microwave circuits, we also know how we can do this T transformation or pi transformation. We can convert a short section of transmission line into a T network or pi network, right? So for example, here I do this pi equivalence. So, and together with negative resistance and positive resistance and the capacitance, then it exactly like I have two active and passive RLC tank. I have a negative ILC tank and a passive ILC tank, and they are coupled. They are capacitive coupled. So amplification and attenuation, gain and loss. So there are several ways to realize PD symmetry in electromagnetic systems. So I'll first start from this case, and I go to this case meta surface, PD symmetric meta surface. So, so if I want to realize a PD system in electronics, I have a microcircuit. It's very easy. So I just need to have a active IOC tank coupled to a passive IOC tank, right? Or I can use a transmission line and lumpy element to realize the system. Or I can realize this inside a waveguide or inside or with a meta surface. I have a two meta surface, active meta surface, negative meta surface. This guy is embedded with negative resistance converter or with amplifier or with op-amp, right? And I'll talk about their application later in sensors, in wireless power transfer, in amplification, filtering, and also super directivity antennas, and also last one I'll talk about the hardware security, cybersecurity applications. So the first one is very simple, just from the circuits 101. It's LC tank, LC sensor, right? It's used everywhere. So for example, this one was done by UC Berkeley. It's a food quality sensor. So they use 3D printer to print the LC tank. And they use another coil, RF coil, to read the LC tank through inductive coupling. So you can measure the resonance frequency shift to tell the pressure inside the food tank, because the spoilage changes the pressure. When the pressure changes, change the capacitance. If I monitor the shift in resonance, this is S11 versus frequency. I know I can retrieve the food quality. It's very, very straightforward. It's nothing special. It's even used everywhere in biomedical application. So we use this for eye pressure sensor. Use a micro machine LC sensor, brain pressure sensors. It's a blood pressure sensor. Cardio. It's a product by CardioMeds. So, and also used in many wearable and implantable application, biomedical wearable application, e-skin. So what's the problem? The problem is they always have very low sensitivity and very low resolution. So it's hard to distinguish the signal. Sensitivity, the shift is very, very tiny, and the Q factor is low because of the loss, the skin effect loss, the dielectric loss, conduction loss, eddy current loss, so on and so forth. So I want to solve the problem with the PD symmetry. So what I want to use is this technique, the exceptional point and the bifurcation effect I mentioned earlier. Okay, so if I look at the sensor structure, is very much similar to wireless sensor structure, very much similar to PT circuit. So this IOC tank is a micro machine, micro nano sensors. And this guy, negative IOC tank, is a reader. And they are coupled inductivities through an inductive link, mutual inductance, basically. So I can write down the quantum analogy. I can write down the eigenstate. I look at the charge and the charge flow on both tanks. Or you can look at the voltage and the current, charge flow, same. Then you can write down effective Hamiltonian based on KVL or KCL. So, and then you can define a Q factor of this guy is a non-hermeticity. It's a Q factor of a tank, right, LC tank. And you can define the carbon strength. It's just a normalized mutual inductance. And indeed, if you apply the PT operator, this Hamiltonian is a non-Hermitian, but you can commute with the PT operator. It means the system can have a real eigenfrequencies. So we have published many papers with my collaborators, and recently we just published a review article in Nature Electronics with Rami Elghanani and Kotos, and so by the backdoor design for the electromagnetic engineer, this is very easy. So it's like we design a voltage control oscillator or a VCO. So in the VCO design, we need a negative resistance, right? It can be a copied oscillator, Hartley oscillator, and we just need a feedback loop. And we need an LC tank to lock the frequency or to lock harmonics, or sometimes we add a phase lock loop as well. So in this case, it's like a higher order copy oscillator. So we have a negative resistance, and then we have two tanks. They are coupled. So you can expect there will be multi-harmonics for this higher order copied oscillator. So we use this VCO structure to realize the system, the sensor system. And this is what we got theoretically. we have exceptional point. This gamma is a Q factor, or non-hermeticity of a system, and kappa is a carbon strength, right? So at this point, you can see the eigenfrequency divided from 1 into 2, and beyond this point, we are in a PD broken phase. Eigenfrequency are complex conjugate pair. But here, it splits very fast, and there's a very sharp slope. So it means I change a little bit the Q factor, I change a lot the eigenfrequencies or the output harmonic or the resonance frequency. So my student took a lot of time to build this micro machine LC sensor for eye pressure management. So the pressure can change the capacitance and change the resonance. And first we tried a conventional approach, just a coil to read the change in the eye pressure and intraocular pressure. So this is a reflection coefficient versus frequency. You see, the change is very, very small, and the modulation depth is very shallow. And then we try this PD symmetric reader. And now you see the Q factor becomes very high, and the shift in resonance becomes very dramatic because we follow this slope. We lock the system around exceptional point, and then we introduce perturbation in the Q, and then you can expect the shifts in resonance frequency follow this locus or this root or this root. So you have two resonance. So we solve the long-standing problem, sensitivity and resolution. And later we also try some new content operator. We do this reciprocal scaling operator, which change the circuit a little bit. But the cool thing is that we change only the circuit topology, but we get a new Hamiltonian. It's a similar matrix of the original Hamiltonian PD system. So they can have the same eigenfrequency but different eigenstates. So with this technique, we maintain the same sensitivity, but we can have very, very sharp resonance, very, very high Q resonance. So we can achieve sub mmHg pressure resolution. And later we extend the system to a higher order PD symmetry system, like Carbot 8 is a multi-atom system, the Bose-Hubbard model. So we derive the generalized equation for the system to calculate the resonance frequency or the eigenfrequencies. And it's a transcendental equation. The root of the transcendental equation is the eigenfrequency. It's very similar to a Chebyshev function, but you can imagine it's for active filter. It took some time to get the generalized theory. And these are new eigenfrequencies. And then I just take this one as an example. So I have a active ILC tank, coupled to ILC tank through many repeater. These are LC tank, neutral LC tank, no loss, no gain. So if I look at the numerator, I can find exceptional point. If I look at the denominator, I found a divergent point. So if kappa equals to this value, this term becomes 0. So once the 2 points hit together, what could happen is that this guy can further amplify the bifurcation effect. So we done some experiments, third order PD symmetric system, and what we observe is that we can amplify the bifurcation effect because we merge divergent points and exceptional point. We call it a divergent exceptional point. So even though the Q factor change, this guy changed a little bit, the resonance can shift dramatically. Okay, this done experimentally. And then we found something interesting. There's an eigenfrequency. This is a normalized eigenfrequency, normalized with respect to the natural frequency of the repeater. So it's basically the unit is 1 over square root of LC. So what we observe is this guy is constant. It's independent of carbon strength. So it means even kappa is very, very small. The carbon is only 0.001. I can remain real eigenfrequency and high transmission efficiency or high power conversion efficiency. And then we do some experiments to test this idea. And what we observe, even kappa is only 0.05. We can have more than 90% transmission. So, or then we can counter we can enhance the distance of wireless propagation, sorry, wireless power transfer. Okay, so I think I have some animation. I can show the animation with the rate. And this is an animal experiment. The rate is jumping and moving, and we can still turn on the LED. So we change the distance between, there's a coil and LED embedded inside the belly of the rate. It was done by some surgeon. And even this guy is moving, we change kappa. Or kappa is very small, we can still have high power transmission efficiency. And later, we also demonstrate this with wearable sensors in collaboration with other group. It's Caltech and University of Missouri. And what we demonstrate is we build this LC sensor. It's e-skin. It can be placed on your skin to monitor the temperature. You see, we put a lot of sensor here. Put temperature, sodium concentration, potassium concentration, pH value, ammonia concentration, and we can monitor. We can use this PT reader to monitor all these important vital signs, and it's very accurate. You can see a huge difference under different scenario. When you are thirsty, or when you are hungry, or when you are full, you see the change. You can also monitor the performance of athletes. So during the exercise, this concentration will change. So what we are trying to do is we have this e-skin on your e-skin sensor on your skin, and we have an NFC reader to integrate the sensor. And Bluetooth module is also on the reader, so we can transmit the information to the server, to the IoT gateway, or to the edge processor. And we also demonstrate this can be used to monitor the glucose concentration and ammonia concentration of diabetes patient under different scenarios. Before, after exercise, before, after meal, with healthy foods, unhealthy food. You can see a difference. And so this is very useful. With my colleague Ahmed and Chetan is trying to analyze the data. We collect all information from the patient. He analyzes the data and to predict the diabetes possibility. So now we just published the paper recently in these journals. And we also demonstrate with the brain pressure during the surgery. So we put the sensor inside the brain of a rate and monitor the change. And with this PD technique, we can amplify the sensitivity. So even the pressure change is very small, we can accurately, robustly detect the change. And it can be used in many different applications, many different bioimplantable devices. I just showcased some here. So we are working with a company in California, CardioRead, to commercialize blood pressure sensors. Okay, then I move to the next topic. It's about PD symmetric meta surface. And it was proposed first by my PhD supervisor, Andre Alou. I was very lucky to be his first student back to 2009. So he proposed if I have a active and a negative meta surface, I pair them together, then I can realize a negative index median. And then I can realize a clock. So around the exception point of the system. And he also demonstrate, we can use this guy, because this guy can be a PT symmetric meta surface system is also a negative index median. And it's a very simple way, and it can counter the effects of dispersion and the loss of metamaterial. It's very important, because metamaterial, people question its performance when we consider loss, when we consider dispersion. And with this, he can just recover the image through the super lens. So if we model the problem is very simple. We have an active meta surface, passive meta surface, and we can use scatter matrix to model it. We can consider forward propagating wave, backward propagating wave coming from different ports. So I put a plus and a minus sign for different ports, right? I put a forward propagating wave and backward propagating wave. So they can be input and output can be modeled with an S matrix. So, and then you can use a very simple, transmission line model to model the problem. So I have a transmission line. and I have two shunt conductance, positive, negative, right, gain and loss, and they are coupled. And and if you study this system, you study the eigenvalue of a scatter matrix, study the eigenvalue of a scatter matrix, and this is what we observe. So we observe there's a transition point, essential point. So as a transition point, as essential point, the two eigenvalue of scatter matrix, they collapse. And then after this essential point, we're in the exact PT phase. So you apply the PT operator to the eigenstates of the scatter matrix, it becomes identical. So we have a unimodular here, unimodular eigenvalues, and we have, so it means the energy is conserved. So in the PT broken phase, what we observe is so the eigenvalue becomes non-unimodular. So one is larger than one, the other is less than one. Means I have an amplification and I have an attenuation. So for this application, eventually focus on essential points and PT symmetry. So I'm focus more on this PT broken phase. If I apply the PT operator to the eigenstate, it becomes another one. So all the eigenvalue, the two eigenvalue, they are reciprocal and follow reciprocal and the complex conjugate relationship. I like this point because one eigenvalue becomes 0, the other becomes infinity. It means it's a laser, and this guy is a coherent, perfect absorber. They can exist at the same time, at the same frequency, and in the same system. Sorry, I forgot to mention here, gamma is a gain loss parameters. It's simply the surface resistance or surface conductance of the meta surface. Okay, so we realize this system with the optical pump graphene meta surface. So you can, there's a theoretical formula. You can have some design guide to design the active graphene meta surface, right? So it shows a negative surface resistance. And I have a lossy metal sheet as a which give you a positive surface resistance. And there's a spacer. So I can if I pump graphene meta surface, then I could have gain, optical gain. Then I can realize a PD system. So I just quickly talk about some detailed properties. So indeed, if you sweep the surface resistance by changing the pumping intensity, what you can observe is the eigenvalue. At the beginning, it was bounded in this circle. It's unimodular. At the exceptional points, then eigenvalue there becomes the reciprocal. So one goes outside the circle, the other goes inside the circles. And so at the exceptional point, so we have a reciprocal transmission equal to 1, which is reciprocal. S21, S12 are the same. And from one pole is reflectionless. The other pole, we have a reflection coefficient equals to 1. And the reason is that we have this unidirectional reflectionist properties. At this point, if you look at the phase of reflection from one pole, the time delay as the phase over partial phase over partial omega becomes infinity. So we can trap the line for infinity time. So we can make unidirectional reflectionist property. So anyway, so I want to talk about this coherent perfect absorber laser. I want to talk about this point. I found several interesting applications. So so now, this was published in Nature Photonics a few years ago. They used a 1D PD system, gain loss, gain loss, gain loss. And then I realized you can simplify design with the meta surface, active meta surface, plus passive meta surface. I can realize this coherent perfect absorber laser. It's very useful in optical application because you see, this is the output. So you see a huge modulation depth, more than 50 dB. So, and in this case, we show if you try to, so I launched wave from 2 ports. I have 2 inputs, and output just a backscattering wave, right? And of course you have, so I launched wave from 2 ports, from port 1 and port 2. And I change the ratio, amplitude ratio of the 2 waves. And then I just assume I fixed the magnitude of this amplitude ratio. I changed the phase. I use phase shifter to create some phase difference. So I switch the phase turn. I see the output can go from lasing to coherent perfect absorber. So output is simply the ratio of outgoing power divided by incoming power, right? So, and then we demonstrate it's indeed possible with meta surface. And why I found something interesting is that I want to use the huge modulation depths. So this is the PT meta surface systems. And I try to introduce a perturbation. So there's a delta Y, it can be resistive perturbation or it can be reactive perturbation, right? So if I introduce small perturbation, I check an output factor, outgoing flux, the ratio of outgoing flux to incoming flux. And this is what I found. So this is a perturbation. This mu is a perturbation. And then mu, the output is mu squared over delta x squared. Delta x is the phase error of this transmission line. Is the phase error of this transmission line. So let's say if the phase error is very small, so at the beginning I set this x equals pi over 2. Now I plus delta x, a small phase offset. Then what I observe is if I make this phase error very, very small, it can amplify the slope. It means the output factor can change very fast if I have a perturbation. And it works for both, you see this 1 over delta x squared slope for both reactive and resistive, resistive and reactive perturbations. And if you just use a conventional Febbraio interferometer, the slope is very, very flat. It changes very slowly. But if you use this coherent perfect absorber laser sensor, output factor as a function of perturbation can go very dramatic. Okay, so we published this idea just theoretically in 2020. And then we demonstrate the idea with a transmission line and lumpy element model. So recently we demonstrated this experimentally. And in collaboration with Oster here and Rami Elgenlaini, we demonstrated the concept. And later we want to implement on chip a single molecule detector. So we hope even it's a single biocell or a single molecule we can detect. So here I just repair the transmission line with a T network, and here is again this is loss, right? So it's a PT lumpy element circuit. So anyway, I'll come skip this one, and I want to also talk about antenna applications. So this is from the scattering problem. I have two meta surface, gain and loss, right? And under this condition, I can reach coherent perfect absorber laser. So let's say if okay, so let's say in this under this condition, for specific surface resistance value, the surface resistance is equal to this guy 1 over square root of 2 times cosine alpha. Alpha is the angle of instance, and this guy phi is the phase delay. Phase delay for wave going from here to here. It's kind of like a cavity, right? So it's kd cosine alpha. If I have an oblique instance, it must be equal to pi over 2. And then this is an equivalent transmission line model. So I indeed observe exceptional point. This is a 2 eigenvalue, eigenvalue 1, eigenvalue 2. And if I make this condition happen, then if you look at the eigenvalue, 1 becomes 1. The other becomes, 1 becomes 0. 1 becomes a 0. Look at this case. This is the second eigenvalue of the scatter matrix. One eigenvalue is 0. The other eigenvalue is infinity. So it allows coherence perfect absorber laser to happen all the time. So alpha is the angle of instance, and gamma is the surface, is a normalized surface resistance of the PT meta surface systems. So and then I realized this guy can be equivalent to a meta material or meta channel, low index or zero index meta material. Instead of launching lines from the top and the bottom, I just launch a line find a port. And then I assume it's a parallel plate waveguide, a parallel plate waveguide. But it's different from conventional. It's not a PC. It's a two meta surface, active meta surface and passive meta surface, and they make a waveguide. And I launch a wave from one port. And then what we realize is at a lasing condition, this is always happen. If impedance looking to the top and impedance looking to the bottom, at any point in this transmission line model, input impedance looking to the top and the input impedance looking into the bottom, the summation should be 0. And so we can have a lasing. Reflection coefficient and transmission coefficient is always infinity. And this is exactly the condition for the transverse resonance relation for waveguide. If I want to find the eigenmode of waveguide, we start from this transverse resonance method, right? So we make input impedance looking to the top and looking at the bottom. The summation is 0, right? So if this is the case, if lasing exists, then there should be a mode for this guy. And you can write down the waveguide dispersion and put this condition into here. And then you get propagation constant beta is k sine alpha. And effective permittivity is sine alpha squared. So alpha is in this case the angle of instance. So if alpha is 0, normal instance, then I get epsilon near 0 or ENZ median. Moreover, this is just a boundary. It's just a boundary condition. It's not a bulky median. So it provides fast guided wave. Fast beta is less than k now, background wave number. So it provides a fast guided wave. It means we could have a leaky wave antenna. But usually leaky wave antenna is we have a attenuation constant. But this case is attenuationless, no attenuation. So I show some example. If there's no attenuation and you can guide a fast wave, it means if I have a large aperture, then antenna's directivity will eventually becomes infinity. So we can calculate dispersion, frequency versus the propagation constant. And this is the real part and the imaginary part. So a spatial condition, tuning the surface resistance on the meta surface, and we have beta equals 0. And then I can try to launch a wave from different angle, get the CPL condition, and then do a different design, launch a wave from the port. Then the new dispersion. I change the surface resistance of the meta surface. Then I can get beta equals to this value or low index median, 0 index, low index. I must say, of course, there's a drawback, and you need to pay for the narrow bandwidth. If you look at dispersion is very sharp. If I have a huge directivity, it means I must sacrifice the bandwidth. So I try to change the length of this leaky wave antenna structure, and the directivity always increases. And here I just connect to a match load. So, and we run some simulation. And of course, it's a very simple question. You can just calculate the eigenmode, the current distribution, and apply the Green's function to calculate the radiation pattern. And you agree well with the simulation results. We can have very, very high gain, very directive band. And by changing the surface impedance, and you can steer the beam. And or this is another example. We put a nice source inside the structure, and you apply the Lorentz reciprocity theorem to calculate the far field radiation, right? And you can also again steer the beam, and the results, theoretical and the numerical results, they agree quite well. So I don't think I have too much time. I'm going to move to the last part of my talk about this cybersecurity using this PD symmetric device. So we know we have 80 billion people in the world, but we can recognize each other's voice because our voice is a very unique analog signal. So maybe I'm thinking about maybe electromagnetic device can talk, antenna can talk, circuit can talk. And if they can talk in a unique way, then it can become an electromagnetic fingerprint. Maybe this can be a new RFID system. So this field is called physical unclonable function. And it was implemented in digital circuits. So people try to assume I have some manufacturing error for 2 chips, and therefore can have a different digital output 101010, and it can become a digital ID. So it was implemented using the arbitrary circuits or ring oscillator. So we count the frequency of sets to get 1 or 0. Or here, this is a multiplexer. We just apply different challenge and to count the time delay. Then we can, every time we change a challenge, we get an output. So we can eventually get a bit string. You can also use band register or other structure and the digital logic. And it based on the manufacturing error in the circuit. So we can get this physical uncountable function. And okay, so my idea is that maybe we can realize this in the PT circuit. So if it's just a conventional NFC IFID module, a coil, coupled to a tank, right? So this is the eigenfrequency, quite flat. And of course, we manufacture like 40 devices, they always have the same eigenfrequencies. And this one is a third order PD symmetric system. And this is the reader, repeater, and this is the RFID tag. And because we look at this point, this is the bifurcation point, exceptional point. And already people challenge this point, the entropy is too high. So your sensor could have a reliability issue. But if we use this guy as an entropy source, true random number generator source, then we could have a new application. Look at this point. If I plot the arrow bar is huge. It's amplified around this singular point. And if I'm away from this point, the arrow bar is very, very small. Okay, so we published this work earlier in Nature Communication and Science Elements, and we did some Monte Carlo simulation. We simulated 1,000 devices. We assume the capacitance follows the Gaussian distribution. They are manufacturing error. And you see around the exceptional point, the probability of repeated detection is almost 0, almost impossible. But if I'm away from this point, I can always detect the eigen values. So the thing is that we launch a pulse to this system, and the system can output harmonics. And it's random because we lock the system at this point, singular point. And output harmonic can be very random. Then with the SAR ADC or flash ADC who digitize the RF signal, then we get a bit map. So this map show you this is number of bits, this is number of device. So we have let's say we have 100 tags, and they could have a very different bit sequence. So like the implementation, just a very quick example is I launched a pulse to the RFID tag. RFID tag can backscatter randomized RF signal. So I think I have some, oh, no, not here. Oh, I missed some, oh, here. So like this. So I just take 40 different tags. I use the same reader to read 40 different tags. So I have a very randomized electromagnetic fingerprint, right? Because this guy can output at least 3 harmonics, and they are randomly distributed 3. And this is a combination of 3 harmonics, temporal response. And then I do some statistical model to study the Shalom entropy. Ideally, there should be 1. It's just conventional RFID system, it didn't work at all. And this is the Hamming window. It should be 0.05, means the 2 bit sequence, they are not correlated. And if I try to look at the PT setup, I have very high entropy, almost 1 Shalom entropy in the bit map. And for the Hamming window, this is the mean value, is close to the ideal value of 0.5, and standard deviation is also very close to the ideal value of 0. Okay, and we pass all the needs random number test suit. And we also calculate the encoding capacity. It can be up to 234 bits. And just give you some number, for the C1 Gen 2 RFID protocol, it only give you like with digital memory, you want to give you 96 bits. Moreover, hacker cannot attack the problem because the on-demand generation of encryption key. I need to launch a pulse to the tag, and the tag can backscatter the encryption key. So if I don't use it, then the key will be not stored in the digital memory. So this is a memory-free, digital memory-free RFID tag. Okay, so just let me quickly go through. And this work was highlighted by National Science Foundation in US. They said, oh, maybe with quantum physics, we can secure a future wireless device. And currently, we are trying to use an RFID technique to tap out the PT on chip. And this is our chip. It's very, very tiny. It's only 1 millimeter by 1 millimeter. And it can create a random number, a true random. It's a true random number generator. And so after this distinguished lecture series, I'm going to talk to the CTO of Analog Device. They want to commercialize this technology. Hopefully, in the future, you can see our chip in your NFC device or mobile devices. Okay, so we haven't published a result, but with the RFID technique. And unlike traditional PUF, we don't need a 40 nanometer, 2 nanometer process. We just use a TSMC's old process, very cheap, mature process, 180 nanometer process to tap out the chip. And we can also do this for the meta surface design. And we lock the meta surface as coherent, perfect absorber point, and look at the output. And sometimes it can be a laser. Sometimes it could be a coherent absorber, and the resonance is shifted. Then, in this case, we can digitize the frequency domain response, the spectral response, to get a bit map. So we have a different PT meta surface, and we lock the PT meta surface as a coherent, perfect absorber point. So, and again, as I showed earlier, when I make the PT meta surface, if there's a phase error, it amplifies the entropy. The output response could be very different if I sweep the delta X is the phase error, or I sweep the delta G is the difference in the surface resistance. Of course, if I have a manufacturing error, I cannot guarantee each meta surface has the same surface resistance, or each PT meta surface set, they have the same phase delay between the two meta surfaces. Okay, so thanks to this stochastic behavior, then we can also generate a random number from the frequency domain response. And we get, you see, this bit map is quite randomized, and we implement the device. And this is the entropy close to 1 for entropy along X or entropy along Y direction. And Hamming window, inter-device Hamming distance the mean value is around 0.5. And this is the key versus, this is just a classification. So we want to make sure outside this diagonal line, the mean value of inter-device Hamming distance is 0.5. Okay, and this is just a Febbraio interferometer. We have a Febbraio cavity, and then you see a very poor response and very poor entropy. And the mean value of inter-device Hamming distance is only 0.1. So my colleague, Anis Chetan, he's an expert in AI, so he tried to use an AI model to run a machine learning attack, and he realized even AI cannot generate identical encryption key. The key generated by AI are incorrelated with the key generated by our PUF system or electromagnetic unclonable system. Oh, he also used a Fourier regression model. Again, AI cannot predict the random key generated by our systems. And so what's the next step? Next step, we are trying to secure RIS. You know, there could be a possibility, there could be fake RIS. So fake RIS can collect your information. And so we need to do case identification or authentication for RIS, or anti-counterfeiting for the RIS. So we are building a non-Hermitian meta surface. This is done in my lab. We already built 6. And they have a very unique EM fingerprint. We haven't published the results yet. We're going to get more data. So next is we want to apply this to a RIS, a non-Hermitian meta surface, give you unique EM fingerprint for the authentication of a RIS. And we are also working with silicon photonics to protect the blockchain, protect interconnect for AI server. So we can use PT symmetric optics integrated with silicon photonic integrated circuit to create a random number, to create an encryption key. Use a silicon photonics approach. And we also work on some chips, some graphene chips to create this electromagnetic fingerprint. This is a secure NFC tag. It's recently done in our lab. It was published just recently. And so we have, I'm going to skip this one. And this is maybe the last two slides on my talk. So we built a graphene transistor. And graphene is a nanomaterial, and it's not quite stable. So you have very randomized. It's a single layer or a monolayer of carbon atom. So if there's any defect or impurity, it changes a lot. It's a carrier mobility. It changes a lot. Subthreshold swing changes a lot. It's a Dirac point or charge neutral point. And so we use the graphene transistor and build a RF doubler, and we see a very randomized RF output signal if we tap out a chip. And then we want to use this property combined with the PT to make a new type of NFC or RFID encryption keys. So the idea is this. So here we use this. We replace the capacitor with a graphene transistor quantum capacitance. And the quantum capacitance is very sensitive to electrostatic gating or chemical doping. So it becomes reconfigurable. For example, we apply different gas bias. This is a button gas device. And we can change the temporal response. For this, I show you two labels and under two different bias voltage. So we can have a reconfigurable bit maps. We can reconfigurable encryption keys. All right, so to summarize my talk, I present PD symmetric electromagnetics or non-Hermitian electromagnetics. And I first show the application in sensing, and then I show the application in coherent perfect absorber laser, and in monochromatic, I just use a single frequency. I detect the modulation depths. Monochromatic electromagnetic sensor with high sensitivity. I show a super directive antenna, of course, it's narrow band. I show its application in hardware security. All right. Finally, I'd like to thank all my previous PhD students and my current PhD student to make this work happen. Thank you very much.
Thank you very much for your interesting presentation with a lot of possible applications that are just already there. So the presentation is open for questions. Federico?
Thank you very much. I have a question about the unclonable functions. No?
Yes.
So what is the data rate you reach of generating random numbers, the power consumption, and the entropy? You see is almost 1, but we know that even 0.999 is not sufficient to pass all the NIST test, no? So you have some fail in your NIST report.
Yes.
Can you comment? So how much is close to 1?
Oh, this is actually a very good question.
So you have some fail, no?
Yes.
So, but the first question is about data rate, please.
The first question is data rate. We just use a statistic method. So we get the mean value and the standard deviation from the Hamming window. And from then we just try to retrieve the maximum number of bits. So far we can have 234 bits. It's based on the results from the Hamming window. And so for this NIST test, I think we just look at this, there's a p-value. If you pass a certain threshold, it means you just pass it. And this part, I'm not quite familiar with the NIST test suite. I just, my student run it. I know there are 14 different indicators, and you just pass all the indicators. Yeah, there's a threshold. And but I would say this is a very good question, very good comment. Of course, entropy cannot be one. One is perfect, true random number generator. If I remember correctly, the average value is like 93% to 94%, almost one, but not exactly one. Yeah, 100%.
And the data rate you are able to generate with this technique, so how many random bit per second?
Yes, 234 bits.
200 and?
234 bits. So how I generate this data rate?
Bit per second.
Okay. No. It depends on the RF frequency. So, sorry. This is the temporal response. We design a fresh ADC or the SAR ADC. It's very fast ADC, and we try different sample rate. And you can change the sample rate, and eventually your encoding capacity will saturate. Yeah. So I think so far what we can guess is the 250 bits, and the rate depends on the frequency. If you use let's say 2.4 gigahertz, and or like a RFI mimic, you go to millimeter wave, it can be very fast, easily generated. And people attack from outside, they can. It's very difficult to use a electromagnetic side channel attack to probe the information. If you use an arbiter, you have a very clear pattern to power on and power off. But if you use a very fast, high-speed signal, it's difficult to probe the information. So we hope this can be used in credit card verification. Okay. And so for this one, the power is.
The power consumption, of course, depends on the speed. So if you have to build an ADC,
yes.
So if you go to millimeter waves, you have a lot of power consumption. So it depends on the data rate. It's related like any digital system, no?
That's correct. Yeah, this again a very good question. So if I use millimeter wave ADC is a problem. I need to use a time interleave ADC. And time interleave ADC is not easy.
Since going back to the introductory slide of this topic, you show several other approaches, like for example the ring oscillator, which is let's say by nature driven by noise, and noise in device is a quantum mechanism, no? So they claim for quite low power consumption, or in any case, it's there are also chaotic systems. There are a lot of systems that can compete on this very interesting topic. How do you evaluate your approach with respect to the already existent state of the art?
So when I talk to the company, they say they must use, for example, this AI chip, AMD, they also have a PUF, but they use a 2 nanometer process or 7 nanometer process because it's very random. Digital circuit is usually very robust. But we use analog circuit, so we don't need to use a very advanced process. I don't think everyone can use a 2 nanometer, 7 nanometer process. So we use a 180 nanometer process, so it's very low cost. And we don't need a bunch of, maybe they need to have, if you use arbiter, maybe easily you can even go to 3,000 transistors. But with our circuit, we just need a very few transistors. I can quickly count. Here we have a cross-couple pair to create negative resistance. Maybe just follow a current, some current follower, not too much. Maybe I would say less than 20 transistors, we can make this happen. And because we have very low, small number of transistors, the power consumption in this case is, I think now it's 40 to 60 milliwatts, but we can further reduce. Yeah, the power consumption. Yeah, I talked to the company. They say their power consumption now goes from 10 milliwatt to 80 milliwatts. Of course, we are trying our best to reduce it. I think the good thing is that we need a very few number of transistors, and we don't need an advanced process. We use the singular point in RF circuit, analog circuit to achieve this goal. Yeah. Are you working on this hardware security?
More or less.
Oh, okay. I want to talk to you more. I just studied this recently. Okay.
Okay. Other questions? Just curiosity about the wearable circuit for testing. You say that you can test different parameters. Which one?
We can test, for example, here we can test temperature.
Okay.
Temperature resistive sensor, and this one we can take a sodium concentration.
Sodium from the sweat.
Sodium ion. And this one is a barretter. And this one we have a reference electrode, sensor electrode. And the change in sodium concentration will create a chemical potential to bias the barretter. So we change the capacitance. Yeah. So we have so far we have a sodium, potassium, glucose, ammonia, pH, temperature.
And glucose, you mean
yes.
from the skin you are able to measure because
if you
it's inside.
Sweat, yeah.
So it is a measure that it is reliable. I mean, because this is a very important measurement for people with diabetes. So it is very impacting on the society.
Yes.
And I think if someone is able to manufacture something reliable, it's a good business too. So
Yes.
what is the accuracy you can obtain from the skin?
So this is again an excellent comment, and I don't have an exact answer yet because the problem is we can monitor it, but we don't know. Maybe this value is high for you, but it's low for another people.
You can see the variation
individuals.
during the day,
Yes.
but not so much the real quantity. This is
Yes, and the other thing is there are some noise, too many ions.
yeah. And the outside, it is much more people than taking blood directly.
And the
maybe.
change in temperature or this blood flow can affect.
Yeah, of course.
And so I just give this work to my collaborator. So my collaborator is a famous guy, Ahmed and Chetan. He's working on AI. He's going to analyze a lot of data to make a conclusion. Yeah, this beyond my capability. I just collect the data for them, but I don't know what's the threshold. And but I can see the change, but I cannot judge whether this guy is sick or not. And we need to have more data. We need to set the database first. And maybe machine learning, deep learning can help.
Oh, this is very interesting, of course. Okay, other questions? So, if it's not, I think we can go to the lunch. I would like to, yes, please? Before lunch, group photo. And I take also the occasion to thank Professor Paolo Mezzanotte because he's organized all the things here and also the meet. So, thank you. So now for the group photograph, please.
Siete pronti? Ok. We can start the afternoon session with the speech of Professor Cristiano Tommassoni. Professor Tommassoni is at the University of Perugia and is a fellow of IEEE. He serves as the chair of the MTT5 Filters Technical Committee of the International Micro MTTS. Currently, he is a distinguished lecturer for the IEEE MTTS. He is the chair of the IEEE Italy section joint chapter AP3 MTT 17 Center and South Italy. From 2018 to 2022, he is served as an associate editor for the IEEE Transaction on Microwave Theory and Techniques. Professor Tommassoni is also the recipient of the 2012 Microwave Prize, awarded by the IEEE Microwave Theory and Technique Society. Please, the stage is yours.
Okay, thank you, Paolo. So, I'm actually a distinguished lecturer for MTT, but this is for AP, so I'm an host here. And I'm very pleased to be here with friends because I know them. With Levent, we did something in common. Now, I'm here not as a distinguished lecturer, but just as a private, as a professor of the University of Perugia, I say. Okay, so the title of my talk is Additive Manufacturing, Emerging Opportunities for Microwave Components. This is the summary of my presentation, and we will see how to exploit the additive manufacturing for microwave components. Indeed, this technology was born not particularly for microwave applications. And we will see also the importance of selecting the right additive manufacturing technology according to the application, and the importance of an additive manufacturing-oriented design, as well as the importance of post-processing. We will see this through three examples, through an example in three different technologies. In particular, yes? Ah, okay. Let's also ask for the confirmation if they can hear.
Can you hear me from Teams?
Okay.
Thank you.
Okay. So, it doesn't work anymore. Okay, now it's working. Okay, as I said, we will see this through example in three different technologies: the stereolithography, the lithography-based ceramic manufacturing, and the selective laser melting. So there are a lot of different additive manufacturing technologies, actually. Indeed, in 2010, the American Society for Testing and Materials decided to categorize all the additive manufacturing technologies into 7 categories. The categories are the one you can see here: vat photoionization, material jetting, binder jetting, material extrusion, powder bed fusion, sheet lamination, and directed energy deposition. Today there is no time to see all of them, but we will see only the vat photopolymerization and the powder bed fusion. So let's start with the vat photopolymerization. In this case, we use resin. Okay. In this case, we use resin which are hardened by using photopolymerization. So, how it works? We have, of course, a VAT, and this is where VAT photopolymerization name comes. And in the VAT, we have a liquid resin. Here is the manufacturer object, which is attached to the build platform. And you can see here the build platform in real machinery. This is the manufacturer object. This is the VAT with the resin. So above the VAT, there is an orientable mirror which redirects the laser in order to create the layer. So the first step is that the build platform is lowered from the top to the resin vat, and then with the laser we harden selectively the resin we need to be hardened for the manufacturing of the object, and then the platform is raised, and with a blade in general we remove all the bubbles inside the resin liquid, because when you insert the object you can insert also bubbles that if you don't remove the bubbles, the air bubbles, you will have holes in your manufactured object. So the process is then repeated until the manufacturing is completed, and is completed layer by layer. Okay, so now let's see the first technology which falls in this category, the stereolithography. So the stereolithography, of course, falls in the category of VAT photopolymerization, the one we have seen now. And then we, as I said, we can harden this photopolymer by using a laser. And one of the characteristics of this technology, but not only of this technology, in general for additive manufacturing technology, is the versatility. So this gives us the opportunity to think to completely new geometries, so components with non-conventional geometries like this one, for example, or this one, that can be manufactured very hardly by using the traditional technology. In this case, you cannot manufacture in just one shot. You have to attach this part later, and then you have to make this post separately and then to join. In this case, instead, it is much easier. And by the way, as I said, there is not only the stereolithography capable of that. In general, all additive manufacturing technologies. The accuracy of this technology, however, are quite good, because the resolution ranges from 25 to 50 micrometer. And it is low cost, because the machinery is about $2,000, I think, we paid our machine. And the resin also, it doesn't cost so much. So it is affordable, at least for a laboratory, is really affordable. And then it is also easy to use, because it is plug and play. And this is not something that happens for all additive manufacturing technologies. So this allows fast prototyping. When you have, for example, an idea, you can design something, and the day after you have the prototype. Unfortunately, we have limited mechanical performances, because this is plastic at the end. So it is susceptible to deformation under temperature, and it is not so hard. So let's start now with the first application. This is a filter, a mushroom-shaped post filter, which developed here in our university, that has some interesting characteristics, and we use a cavity loaded by a post, a mushroom-shaped post, and this is to obtain a very small structure. And then you can see that there is a complex network of wires, you can see here. And with this, we are able to control the characteristics of the response. For example, if just take this structure and we change this 8, like here, you can see that we can control the filter bandwidth. Then this, all the part of this structure, for example, this 8, this length, and so on, control other characteristics of the response. So, for example, you can control the position of the transmission zeros. There is no time to explain now how it works, but now I want just to show how to manufacture this with this technology. Okay, let's start with some observation. First of all, when we use additive manufacturing, we generally need supporting structures. Indeed, we need supporting structure for the part of the object which is not self-supporting. I explain later what does it mean. The manufacturing tilt must be also carefully considered because this impact on the supporting structures and also impacts on the accuracy, on the at the end on the resolution of the object. So, and another important thing to point out is the importance of the additive manufacturing oriented design. This means that when you are using additive manufacturing, you cannot just recycle old projects, but you have to adapt to this technology. Okay, this is the manufactured filter, as you can see. And I want to show why it is important to have supporting structures. Indeed, when we manufacture this layer, consider that this manufacturing is from the top to the bottom. When we are trying to manufacture this layer, we have not a previous layer to attach this part. That's why we use the holding structure here to support this layer. Otherwise, you cannot attach to the previous layers. For example, here, when we manufacture this, here, it is not needed additional, they are not needed additional holding structure because we can attach this layer to the previous one. And you can see also here the importance of the tilt. Indeed, with this tilt, we can obtain this part without adding additional holding structure. But if instead of this position we use a position like this, you have to add also inserting structure, holding structure here. So you can see that the tilt angle influences also the number of holding structure. And holding structure, when you remove it, can leave bumps. So it is better to minimize them if possible. So let's have a look at the post-processing. Well, in this case, for this technology, we need a post-processing that consists in washing the object by using alcohol inside here. And then this allows us to remove the not solidified liquid because it's very dense. So when you touch it, it's very sticky. With the alcohol, you can remove it. Then it is not mandatory, but it is advised to cure the material by using ultraviolet light. So there is an ultraviolet oven that may improve the material quality. And then you have to remove supporting structures. As you can see here, we have removed. You can see the supporting structure here, and here they have been removed. Okay, this is the post-processing related directly to the technology. Then we have also another post-processing which is related to our application to microwave. Indeed, we have some specific post-processing for microwave application because this is plastic, we have seen. You can use also as an electric material because this is plastic, but losses are not so good. So usually we use this to mimic the metal. So in order to make it mimic the metal, you need to metallize the object. And for metallizing it, we use electroplating. The electroplating is done in 2 steps. In the first step, we spray the object with a silver paint to make it conductive. The silver paint is not so good in terms of resistivity. The resistivity is quite high. And then we prefer to use this layer to add another layer of copper by using electroplating. This is because with electroplating we can obtain very good results in terms of losses because the conductivity of the electroplated copper is very high. Then what is the problem? The problem is that if you have to metallize these things, you have to manufacture in two pieces. As you can see here we have, the cavities and then here the base. And we cannot manufacture it in monolithically in just one shot because we have to metallize the internal part. So we have to, we should have the possibility to spray the paint. So that's why it is not possible monolithic manufacturing. Of course, other metallization method can be used. For example, the electroless plating, in which you can metallize an object just by inserting it into a liquid, and with some chemical reaction, you can obtain the results of metallizing the walls. But also in this case, there are, in this case, perhaps you can also manufacture the object monolithically. But in order to allow the liquid to enter the object, in any case, you have to put slots. And so you don't have the problem of manufacturing two pieces, but you have other problems. And this is an example. This is monolithic. But as you can see, there are a lot of slots in order to facilitate the liquid to enter inside. So there are pros and cons. Okay, let's see the final manufactured object. This is the comparison between the measurement and the theoretical response. And what I want to point out is that here we have a complex network of wires, which, thanks to the flexibility, thanks to the flexibility of this technology, we can manufacture in a single shot. So it is not necessary to manufacture this and then attach it. It is directly obtained with manufacturing. So this is the main advantage in this case. Okay, now let's go to another technology, the lithography-based ceramic manufacturing. In that case, also in that case, we fall in the same category of the previous one, the VAT photopolymerization. In this case, however, we have a photoreactive organic binder, which is the liquid, the photoreactive liquid as before. But in this case, in addition, we have alumina powder suspended in this liquid. So we have this mix of liquid photopolymer and this powder of alumina. This liquid with the powder is called slurry. The slurry is then hardened layer by layer like in the previous technology. But in this case, when it's hardened, it contains also alumina. And when we manufacture this part, we call it a green body, even if it is white, but it is called green body. I don't know why. Now, for this technology, we need another particular post-processing. Indeed, the green body needs a thermal post-processing, and we have to warm up to 1,600 degrees. And during this phase, we have a shrinkage of about 20%. So this must be taken into account. Anyway, what I like very much of this technology is that at the end, we have a ceramic material which incredible microwave properties. For example, the loss tangent is about 8 up multiplied by 10 up to minus 5. That is the one of the regular alumina. So it is very surprising that after this process, you can obtain something very equal, let's say, to the pure alumina. At the beginning, actually, I thought that was a mistake because the company we are collaborating with, they are not expert in microwave. So I said, but how did you find this? I don't think it is possible. But we measured it ourselves, and we have seen that actually this is the results they reach. Then the problem of this technology is that the price is quite high in this case. It's not cheap. And it is not plug and play. So in this case, it is better to have an experienced operator which can help you in the manufacturing. And this is the scheme of the machinery produced in Litos. Litos is the company which we collaborated in for some filters. And Litos produces the 3D printing. So they have not specific competence on microwave, but they are interested to collaborate with experts in microwave to see if it is possible another market for them. Consider that the microwave market is not the main, the main market for them. It's just a lateral market. But anyway, they are interested. So how it works? Well, scheme is more or less what we have already seen, in which we have a bath, and then the photopolymer with the addition of this alumina powder, and then the manufactured object again, which is attached to the build platform. But what is actually very interesting in this technology is the optic system. Indeed, instead of having a mirror which redirects the laser, here we have an optic system that projects directly, the imaging of the layer directly on the vat. So this means that you have not to scan to obtain the layer, but you obtain just in one shot. So this is much more rapid. I would like to spend a couple of words about the thermal post-processing to understand how it works. Okay, this is the green body. And if you see what happens, the material of the green body is, as you can see, is composed by ceramic particles, the one in yellow, green, I don't know how to define here. And then we have the photopolymer. The photopolymer is the one that allowed us to harden this part. So it is very important in the manufacturing. But then we would like to get rid of this because we want just to have alumina at the end. So in the first phase, there is we increase the temperature in order to do the so-called debinding. Indeed, in this phase, thanks to the temperature, we can get rid of particles of this polymer. But it is not enough because, as you can see, there is a lot of empty space between particles, and this is not good for a dielectric. Indeed, this may also increase the losses, even if it is not so clear, because you say, okay, but this is space, free space, why increases the losses? But for the interaction of grains, grains is the name they use for a single particle of the ceramic. And so it is better to remove also this space, also because the material became more solid. And so we passed to the last phase, in which we increased the temperature up to 1,600 degrees in order to sinterize the alumina. And consider that this is the regular procedure that has been used for thousands of years. I mean, if you see the technology of the ceramic, when you manufacture pottery and vase and so on, you use the sintering, you put in the oven. This is the same. So thanks to the temperature, you can obtain a compact structure with no hair inside, or a limited quantity of hair. But as you can see, during this process, you have a shrinkage of 20%, and this must be taken into account. Fortunately, this is quite, it is possible to forecast it quite accurately. So this is a Litos Litho's video, in which they show the procedure. As you can see here, instead of moving the blade, they rotate the vat in order to remove bubbles. But this is the slurry arriving inserted to the vat. Again, we remove all the bubbles by taking the vat, and this is the optical system. And as you can see, the optical system projects directly the image of the layer. So in one shot, you can obtain the layer instead of scanning with the laser. So this makes this procedure faster. Once the manufacturing is finished, you have to take the object to clean it up, as you can see. Then this is the phase of the post-processing, in which you increase the temperature in order to sinterize the object. And as you can see, this is a typical RF application. No, this is a medical application. Indeed, because as I said, our market is not so important like, for example, the medical one. They use for tools and so on. Okay. Now I will show what we did with this technology. Also in this case, like in the previous one, we have a dielectric material, but we have seen that behavior in terms of losses is much better. So in this case, we use this alumina material to manufacture a filter by using this material as a dielectric, as a resonator. One of the problems of the dielectric filter which uses dielectric, is that you cannot touch with the dielectric the metal. I mean, if you want to obtain a good resonator by using dielectric, you cannot use in the free space, because otherwise it radiates. So this is not good because there are a lot of losses for radiation. So you have to put inside a metallic enclosure. But when you put in a metallic enclosure, you prevent the radiation, so it's very good, but you cannot just put on the floor of the metal, because in this case, what happens? That the electric concentrate inside the field. And that's why we use it, because this allows also to shrink the object. But the concentration of the field inside is very high, and is very high also on the boundary. So if you touch directly with the metal, you increase the losses, so that's not good. So you have to suspend it. In traditional technology, you can use a low dielectric material, which can make that can hold this high dielectric material. This means that if you use a dielectric material with a low dielectric constant, the field is not concentrated in the base; it's still concentrated in the resonator. So you can avoid, you can decrease the losses. Well, in this case, but if you use this pedestal, in any case, you have to glue it, so you have problems. You have to glue it, and glue is not good for a lot of reasons, and so on. So in this case, we try to exploit the flexibility of additive manufacturing technology in order to avoid this pedestal. Well, with traditional technologies, it is not so easy to manufacture something like that. If you ask to a company to do something like that, they manufacture this, and they glue. But again, we have glue. So in this case, our idea was, in order to maintain this dielectric suspended, we can use branches, and then to anchor this resonator here. Consider that the field is concentrated here, not here, so we can touch this part with the metal. But this is suspended. So this was the idea. And we tried this in collaboration with RF Microtech, and was a European Space Agency project. And this is the result, in which you can see the comparison between simulations and measurements. This is for a 4-pole. Then we manufactured a 6-pole filter in 2 layers. As you can see here, there are 3 resonators and 3 resonators. And this is the results for the 2 prototypes we manufactured. But this was for the European Space Agency. So each component you are supposed to send in the space needs space qualification. So we have some space qualification tests. I can show some results. For example, the thermal cycle, indeed, when we have a satellite that goes around the Earth, sometimes it is in the shadow of the Earth, sometimes it's in the sunshine, and the temperature changes a lot. You have to guarantee that this change of temperature doesn't break, doesn't damage the components. And this is this test. This is before and after this temperature cycle, and as you can see, the response is almost the same, so it's not damaged. But not only you have to avoid the damages, but you have to work at different temperatures. So that's why we have also tested the temperature stability, in which we have seen how changes the response with the temperature from minus 25 degrees to 75 degrees. This is what they require. And we have seen that we are inside the specification. There is a small change in the response, but we are still, we still fulfill the specifications. And then there are also mechanical tests, because when you send the component into the space, you have to put in a rocket, inside the rocket, and the rocket is very noisy. I don't know if it happens to you to see a launch of the rockets. I have seen from 3 miles of distance, but the noise is incredible. I cannot imagine what happens inside. And for that, you need to do a vibration test. And as you can see, survive to the vibration test and also to the shock test. Okay, this is another filter we did with the same technology, with the same additive manufacturing technology, but here the idea behind this was different. This is, again, a European Space Agency project made in collaboration with RF Microtech, and that was the idea. One of the problems of the filter with dielectrics is that we can obtain only narrow band filters. What does it mean? It means that if you have 2 resonators, in order to obtain a wide band resonator, you need 2 resonators that are able to exchange a lot of energy, let's say. If you use 2 dielectric resonators, the field is concentrated inside the resonator, so they don't exchange a lot of energy. And this results in narrow band. So you can use filter only for narrow band application. This is a limitation of this kind of filters. So our idea was instead, by exploiting the flexibility of the additive manufacturing, we can use different geometries, and for example, we can use a complex geometry like this, in which here we have the first resonator, here the second, but we also manufacture a sort of bridge, again in alumina, in order to facilitate the exchange of energy. This increases the coupling between the 2 resonators, and this allowed the wideband result. Indeed, as you can see here, we obtain a fractional bandwidth of 44%. That is much higher than usually. Usually they reach 1%, 2%. This is with this idea. Indeed, we was able to overcome this problem. Okay. Now some consideration about the additive manufacturing oriented design. But first of all, we have seen that we have the post-processing phase, and it is clear that you cannot do what you want, because, for example, when you remove your object, you have should have the possibility to clean it up. So if you, for example, make an hollow sphere without holes, you cannot clean inside. So you have to pay attention to this, of course. But this is clear. What it is less clear is that you have to avoid instead some shapes that can result in cracks during the sintering phase. This is not so obvious, but if you are cooperating with a person which has expert on this technology, on additive manufacturing technology, when you design your component, they can say, okay, it is better to avoid this shape. Can you change it? And then it is also important a proper distribution of the weight, because during the shrinkage, some deformation may occur. This is what we learned at our expenses, because we didn't know that, but we realized that you have to pay attention. Indeed, this is one object we manufactured, and this is another, in which you can see that they are deformed. Well, why they are deformed? Because consider that there is a shrinkage, and if you put a lot of weight in the external part, when there is a shrinkage, the part which is very bulky cannot follow the shrinkage, so it deforms the object. So in order to solve this problem, this is the anchor point to the waveguide we have seen before and also here. So the solution was just to make this part lighter. And this is what we have done for this component. And instead, this is what we have done for this. So this is an additive manufacturing oriented design. Please. As you can see, we understood later. No, probably if you insert in a simulation in which you know what is the grip and so on, you can also understand what you can do and what cannot do. In this case, it was very easy to remove the bulky part, so we didn't do additional studies on that. Probably it is possible, but in this case was not so useful. But I think it is possible. Here, instead, for this design, we changed the way we started, because here, this is the resonator for the filter we have already seen. And at the beginning, we start with the idea to manufacture more than one resonator together with the other. So unique block containing all the resonator or part of resonator. We have seen that this is not possible, so we passed to this solution in which we have each single resonator with each branch. So this is an example of additive manufacturing oriented design. Now let's go to the second category of additive manufacturing, the powder bed fusion. In this case, we have powder and an electron beam which melts this powder. So when the powder cooled down, it became solid. So this is the idea. Here we have the so-called powder bed. We manufacture the object inside this powder bed. We will see how. This is the build platform. In the real 3D printing, here we have, this is the build platform, and the powder bed goes here. Now there is no powder. And then here we have the new powder stock, this one. Here we have the powder roller, this one. And again, we have a mirror above that redirects the high power laser in order to create the shape. But let's see how it works. Well, first of all, with the laser, we melt selectively the powder in order to create the shape we like. Then a new powder platform is raised while the build platform is lowered, as you can see here. And then, by using the powder roller, we can create another layer of powder, and this allows us to make another layer of the object by using the laser. So, layer by layer, we can obtain the final object. Okay, now let's see one of the technologies falling in this category, the selective laser melting. Well, in this case, we use metal powder. So we need a high-power laser in order to melt it. And considering that this is metal powder, at the end we obtain a metal object. This means that now the mechanical performance are very good. It's not like for the plastic. Here we have metal. And it is also allowed monolithic manufacturing, as you can see here. Here, this one is a filter, and the interesting part is inside the cavity. But we manufacture it monolithically. And this is a very good advantage, because if you would like to manufacture something like this or this, by using traditional technology, you have to manufacture in two pieces, because you have to the traditional technology is a milling techniques in which you remove material. And in order to remove internal material, you have to cut in two parts, make the cavity, and then the other part, and then to assemble it together. But if you do that, you need flanges, for example, and you increase the weight. You need screws, and then so you increase the bulkiness of the structure. Not only, you have problems also because when you join two parts, they are there, but you need a lot of pressure to obtain good results. You can see that this increases the losses in some way, because of the ohmic contact is not so good when you separate in two parts. And then you risk also the PIM and so on. So the monolithically manufacturing is for sure an advantage. And we can do it because this is already metal, so we don't need to metallize it. The accuracy also in this case is quite good. It ranges from 25 to 100 micrometers. It depends on the part you are manufacturing. And unfortunately, also in this case, the cost is relatively high. Yeah, we are talking about, I think, some $100,000 of dollars. And it is not plug and play again, because you have to set several parameters. For example, just to give you an idea, the laser, the power of the laser. If you put too much power, you fuse a spot which is larger, and the resolution is not so good. If it is not enough, perhaps you don't fuse completely the powder, so you can see at the microscope that the solid particle just are stick, but you can see all the air between particles, and this is not good again for in terms of losses, because to have this stick powder is not good also for the as a mechanical behavior. So there are a lot of things to be considered. And then the metal powder is dangerous because it's very thin, the powder, and then it may explode because it can react with the oxygen. Indeed, inside this machinery, they use argon. They work with argon and so on. And then it is dangerous also because you can inhale, and this is a problem for cancer. Indeed, this is Swiss 212, another company I'm collaborating with, and this is what they wear in order to avoid to inhale this this powder. You can see the laser here. This is accelerated, of course. This is not so fast, but after the manufacturing, you have to remove from the machinery, and then you have to remove the residual powder. But this is what you can manufacture, all monolithic and also complex structures. So this is very good, for example, for space technology, because you can avoid flanges, you can avoid a lot of problems with that. Now I show you a component we designed and manufactured with this technology. In this case, it's again a filter. Perhaps you can understand that I'm a filter guy, because I presented now only filter. But the point is that spherical resonator are the best in terms of Q factor. They are not new because they are already used. What is new in this filter is that we didn't use the fundamental mode of the cavity, but we use another mode. The fundamental mode is the TM101, and instead we use the TE101. And this allowed us to increase, to decrease a lot the losses, which means that we increased a lot the Q factor, because the Q factor is a figure of merit of losses in resonator. And as you can see, we are able, in different conditions, for example, 10 gigahertz or 22 gigahertz, always to more than double the Q factor. So this is a good resonator, I would say. So now let's see what does it mean, an additive manufacturing oriented design in this case. This is a filter made of two resonators here, spherical resonators, and this is the way you can manufacture traditionally, in which you, for example, you make a hole in order to make in order to allow the exchange of energy between the two resonators, and here we have other aperture that allows the energy to enter from the input and to go out from the output. This is what usually we do in filter technology, but considering that we have to manufacture it by using additive manufacturing, well, it is better to modify a little bit. For example, instead of using this shape, for additive manufacturing it's always better to have chamfered irises, for example, because this is self-supporting. But especially here, you can see the difference, because in this case, consider that when you have to manufacture this aperture, at this point you have to manufacture the top, the rooftop, let's say, of the aperture. If you want to manufacture this, you need a lot of supporting structure, otherwise it collapses. And that's why we modify the aperture from rectangular to ellipsoidal, because ellipsoidal, you can manufacture layer by layer like this, and you obtain like a dome. If you didn't visit when we go in Rome, I show you perhaps the Pantheon, yeah, I didn't get the name. The Pantheon is one of the first realization in which you use this self-supporting structure. Well, and in this case, we were able to avoid internal supporting structure that would be very difficult to be removed at the end, and also compromises the accuracy. And here, the accuracy is very important. Okay, then this is the mechanical design, which we add just the flange, and we also add the pedestals in order to maintain stable the structure during the manufacturing. And this is the fabricated filter. And as you can see, also in this case, we used post-processing. Indeed, when you manufacture an object, you fuse parts that cool down, and then fuse another part that cool down. And when they cool down, they change the dimension, they shrink. So this means that you create internal forces that may deform the object itself. So one post-processing is this so-called stress relieving, in which you warm up the object in order to relieve the stress inside. Then another important, the so-called shot pinning. Indeed, when you manufacture this, the surface roughness is not so good, and then this impact on the losses of the filter. And with the shot pinning, you can instead obtain much better results. In this case, for example, we obtain a Q factor of 7,000 without silver plating. And for what we know, this is the highest Q factor ever reached by using additive manufacturing. Just to work on the shot pinning, and well, in this case, it consists of spherical particles that are shot through the surface, and this create a smoother surface, like the sandblast. The principle is the same of the sandblast. And thanks to this, we pass from a Q factor of about 4,000 to 7,000. So we almost double the Q factor. So it is very important, this post-processing. Here you can see the results for two prototypes. As you can see, there is a shift in frequency between the simulated and the two prototypes. But as you can see, the two prototypes are practically overlapped. This means that there is an error, but this is a systematic error. It's due to the fact that perhaps there is something that collapses a little bit, but it's repeatable. So when you have a repeatable error, you can correct it. So when you know it, you can correct it. This is a four-pole filter instead, in which we use this. Indeed, you can see that this is the third prototype. And the third prototype, because the other two was not good in terms of return loss, was too high. But this was, again, a repeatable error. So we corrected, and now we obtained a filter that, in terms of return loss, is quite acceptable. Okay, until now I showed just results obtained in our laboratory, but I want to show also something else. For example, this filter that has been designed by the group of Peverini in Turin. By the way, in the previous one, we collaborated with them for the manufacturing. And in this case, what was their idea? Here we have three components: a H-plane band, a filter, a low-pass filter, and a twist to change the orientation of the field. So thanks to the versatility of additive manufacturing, they put all together. I mean, here you have a band which allows you to change from this direction to this direction, here. And then we have the filter here, and also the change in polarization, the twist, is all together. So this is a clever way to use the flexibility of additive manufacturing. And this is the manufactured object. As you can see, it's monolithic. That's something that was not possible with traditional technologies. Here you can see the roughness inside because they cut in two pieces. And here you can see the result. I show also this not because it's so particular or interesting, but because this is the first filter flying on a satellite. So this demonstrates that this technology is qualified for space application. This is a filter developed in Airbus by Dr. Booth, and this is actually flying on a satellite. So let's go to the conclusions. Additive manufacturing technology, in my opinion, is very promising. I have shown just X-band and let's say not very high frequency application, but now there are also applications that arrive to terahertz or perhaps sub-terahertz. And so it is a technology that is evolving. Also for the prices of the 3D printing machine, I say that there are some machines that are very high price, but they are the price also is year by year decreases. We have seen that it is possible to use for space application not only the metal but also the alumina components. We have seen that for the metal it allows monolithic manufacturing, which is not possible with classical CNC techniques. And this results in weight reduction because you don't have flanges, no screw, and better RF performances because you have lower losses because the contact is, there is no problem with ohmic contact, and no PIM. And then we have seen also the ceramic additive manufacturing, and this is very interesting because you can use also for space technology, and it is very light with respect to other component. And when you use dielectric, you can also shrink the components. So this could be very interesting. And then additive manufacturing, we have seen, is very flexible, but you cannot do what you like. So my advice is to have always in mind an additive manufacturing oriented design, in which you have to have clear in mind that there are also in that case limitations, and you have to design properly the component. So this ends my presentation. Thank you very much for your attention. I finished a point in advance, but this is just to say that I used to work with expert in 3D technology, because I'm not an expert in additive manufacturing. I'm an expert in microwave. So the collaboration with mechanical expert pays back, let's say.
So we have time for some questions, please.
Thank you. Thank you for your presentation. Very interesting. And I was wondering, with the VAT polymerization and power bed fusion, which kind of level of outgassing are you able to reach? Very low? You have experience with that, or?
Which one?
With both, with VAT and power bed fusion.
No, we didn't try. What I can say is that for the dielectric technology, for example, you may have in general some problems of degassing, but here it seems difficult when you have to do with ceramic, because in the sintering phase you warm up to 1600 degrees, and usually this may disappear the gases. Inside the metal, I don't know what to say, because
no, I was talking about dielectric and ceramic, not metal. Yes. Not in the metal. No problem.
Okay. In ceramic, we have seen that probably there is no problem. There are problems usually with material like Teflon, for example, something like that are manufactured at lower temperature and so on. With this, shouldn't be. Regarding the plastic, the things is more complex. First of all, because until now, they didn't use this for space technology, where the gassing it is important for corona effect and so on. What I can say is that Swiss 212 started testing the plastic for space. So they reached some results. They did some project with the European Space Agency, and they obtained some qualification tests. So they was able to obtain some qualification, not all, but they started this process. So probably it is possible. At a larger expense, I mean, you cannot have the manufacturing at the cheaper price we have here. You have to spend a little bit more, but it seems that plastic are suitable also for the space. But they stop this because they say the problem is, according to them, the problem is not the plastic itself, it's the custom. Because when you propose the custom to use plastic, they say no thanks, we prefer the classic technology. So according to them, it is possible to qualify them. They obtain some results. Okay. They didn't spend more money to obtain also the rest of the results, because they have seen that doesn't pay, at least until now. Because actually, if you are able to overcome the problem of the outgassing, deformation, and so on, it is an advantage to
Yes,
use plastic
absolutely.
because it's lighter.
It's lighter, yes.
So, but at the moment, I don't think there is someone that is trying to qualify it, at least not with the European Space Agency, for what I know.
Okay, thank you for your answer.
Any other question? Okay, I think it's time to go to the next.
Yeah, you can present. Oh. Okay, thank you. Yes. Okay. Okay. So now let's go to the last but not least presentation. The next presentation is from Leven Sergi, and the title is From Engineering Electromagnetics to Electromagnetics Engineering, Teaching, Training, Next Generation.
Thank you.
So, Dr. Levent
Yes.
is an emeritus professor at the Istanbul Technical University. He's an IEEE fellow and the recipient of IEEE APS Chen Tai Distinguished Educator Awards. During his career, he was with several university and research institutes in Turkey, USA, and Canada. And he serves for a year as a IEEE APS Distinguished Lecturer. And now he is the chair of the Distinguished Lecture in Antennas and Propagation. And he served in the APS ADCOM, and he serves also in several editorial boards, including IEEE AP Magazine and IEEE Access. So, we are very glad to have you here, and the floor is yours.
Thank you, Cristiano, and thank you for organizing and hosting this workshop. And thanks God, this is the last talk. I took my first electromagnetic course more than 40 years ago, 42, 43 years ago. And life was easy at that time because the title was Engineering Electromagnetics, okay? We saw some antennas. If you live near airports, you see some mechanical scanning antenna systems. And we have long-wave radio broadcast systems. That's it. But today, it's very complicated. And we have seen lots of high-level, highly sophisticated designs, talks since the beginning of this workshop. And that's why we prefer to call it electromagnetic engineering today. So that's why I chose this title, the transformation from engineering electromagnetics to electromagnetic engineering. This is the outline. I'm going to start with showing a few slides about the definition of first engineering, then electromagnetic engineering. And I chose one system level challenging problem, design installation problem as an example. We are lucky because we have Maxwell's equations, which well establish electrodynamics, mathematical foundation of electrodynamics. All the problems you have been hearing since this morning can be handled with two simple equations, what we call Maxwell's equations. The second part is about modeling and numerical simulation of electromagnetic problems, and we will end up with the conclusions and discussions. So before technical presentation, let me show you a few slides about IEEE, since, as Cristiano mentioned, I am the chair of Antennas and Propagation Society's Distinguished Lecture Program Committee, and one of the organizers of such kind of workshops. So IEEE is our international organization, Institute for Electrical and Electronic Engineers. And its structure can be divided into two. It has geographical units and it has technical units. Under geographical units, we have regions, 10 regions all around the world. And under regions, we have sections. So Italy section is under region 8. On the other side, we have technical units, societies. We have 39 societies like Antennas and Propagation Society, MTT, Microwave Theory and Techniques Society, EMC, Electromagnetic Compatibility, GRSS, Geoscience and Remote Sensing, Aerospace and Electronic Systems, and so on. Total of nearly 40 societies. And under societies, we have chapters, local chapters. You can establish chapters with 12 members and then get funds from your societies to organize such kind of activities. And 2 or more societies can come together on certain topics and they form councils like RFID Council. They don't have members, but they use members of different societies, nearby close societies, which we call sister societies. And until the end of last year, the number of worldwide members has reached 500,000. So IEEE has more than 500,000 members today. And these are some of the figures. We have nearly 200,000 student members, 347, nearly 350 sections, nearly 3,000 chapters, student branches, affinity groups like Women in Engineering or Young Professionals, 39 technical societies, and more than 8 million documents in IEEE Explore Digital Library. So IEEE is a rich organization, and its motto is advancing technology for humanity. So we have lots of money. We spend lots of money for students, for scholarships, for travel grants, as well as for humanitarian projects. For example, if you have a small rural village without pure water, without electricity, you can ask for a fund from IEEE, a couple of $1,000, and build a system that brings pure energy, pure water in those villages. Between you and me, the annual budget of IEEE is $1 billion. And maybe 90% of that income comes from digital library, IEEE Explore, from the technical papers, from the conference proceedings, from standards documentation. Only 5 to 10% of the income comes from membership fees. And if you are an IEEE member, and if you want to become MTT member, student member, or AP student member, you just need to pay $1 per year. We sponsor many thousand conferences and published more than 200 transactions, journals, and magazines. This is the website of our program, Antennas and Propagation Society Distinguished Lecturer Program. We have a handbook there which explains all the rules. We post many reports, including reports from local workshops like this one. So, Cristiano, you should write a few-page summary of this event. We will add group photos and then post them on the IEEE website there. So you will become famous, okay? You don't need engineering diploma. And these are our active distinguished lecturers. Different societies have different rules. In AP Society, Antennas and Propagation Society, each active distinguished lecturer serves 3 years, and then they become former distinguished lecturers. Still, They can serve the society depending on the budget once or twice a year. And this is my committee. Nader is my vice chair. We have young professionals, ladies, members from different regions. So diversity is there in terms of gender, age, and region. And I took over the chair of this program just 2 years ago. I started in January 2024. And since then, we have also organized what we call Inter-Society Distinguished Lecture Workshops, ISDLs, in addition to Society DLs. In 2024, we organized 9 inter-society workshops all around the world. Last year, we doubled it in 12 ISDLs in the first half of last year. Some of them are long tours, like the one we have here now in Italy. And these are the second half of last year. So in total, 25 ISDLs last year all around the world. These are the location distribution, so it's quite homogeneous. We cover almost all parts of the world. And we gather some group photos, selfies, lots of selfies. So if you want to be there, just stay until the end of my talk. Have selfie with me, and then we post it there. This is from St. John's, Canada. This is from New Jersey. Lots of pictures, lots of talks. This is from Pretoria, South Africa. Dr. Islam was there with us. Copenhagen, Denmark, with Physics Society. This is Lund University, Sweden. We also had one in Antalya just several months ago in September 2025. This is from Long Island, New York. This is from Sorbonne University, Paris, and also Institut Polytechnique de Paris, 2 days apart from each other. And this year we start with European tour, especially Italy tour. We started with Genoa, then Trento, Bologna. Now we are in Perugia. February 4th, on Wednesday, we will be in La Sapienza, Roma. And February 5th, this last one should be February 5th, Rome Tre University. And this is the flyer from Genoa, group of pictures from Genoa. Then 4 speakers in Trento, University of Trento, and some pictures from there. And now we are here in Perugia, and with 5 esteemed speakers. And then this is for La Sapienza, WeTools announcement, prepared by Cristiano. And then we will have six speakers on Wednesday. Also, the last one will have 7 distinguished lectures in Rome Tre. Basically, mostly about metamaterials. So these are some suggestions for young students. If you want to have a good network, internationally be visible, join IEEE as early as possible. Be student member less than $1. Establish new chapters and branches and get some funds. And you can then invite distinguished lecturers. Okay, so let's start with the technical part and with the engineering, the definition of engineering. So we are engineers, or we will be engineers. We solve problems, okay? Actually, life is problem solving, but only well-defined problems can be solved easily. And depending on the discipline, the definition of the problem solving may be different. For example, if you are a mathematician, showing the existence and uniqueness of the solution is the solution. But if you are an engineer, you need to deal with observable quantities, which means either measurable or computable. So stability and accuracy of the solution is also critical for us, for engineers. We are engineers. We don't seek the best solution, the cheapest one, or the fastest one. Depending on your requirements, we always do optimization, so optimum solutions. If time is critical, you cannot say, I have this much of money, okay? If money is critical, you cannot say, I want this system within 6 months. So optimization is always #1 issue for engineers. We're engineers, we deal with physics, actually real world, which includes physics, chemistry, biology, and we use mathematics, and we speed up with computers. So there is a relation between real world. This is conceptual world. You can conceptually imagine non-physical solutions, non-real world solutions. And this is the terrible one, synthetic environment, because you have both non-physical solutions and non-mathematical solutions in digital environment. So if you do numerical simulations, you have to be very careful. This necessitates to establish an intelligent balance among the theory. If you want to train, teach young next generations strong in terms of engineering, you need to give them enough mathematical background, engineering experience, and numerical simulation capabilities. Also, we need to well understand the meaning of the numbers we use, because we speak with numbers. We either measure or compute. Therefore, fundamental terms and concepts like accuracy, sensitivity, precision, resolution are critical. So always pay attention to the definition of such fundamental terms. And we never give a result with a single number, okay? If you do not state the error and the uncertainty range of your results, it's meaningless. And as Dr. Özlem said, real-life problems are stochastic, which means the results must be probabilistic. You have to give your results with a given confidence limit. For example, if I measure the distance between that wall and that wall, it's going to be, let's say, 21 meters plus or minus 10 centimeters or 10 micrometers. I'm 90% sure or 95% sure that the result is in this region. So if I'm 91% sure, my uncertainty range is this one. But if I want to be 99% sure, so uncertainty range increases. So you have to be very careful when stating numbers, when giving numbers, when speaking with numbers. Real-world problems are not deterministic, are not stationary, are not linear, are not homogeneous, but we assume they are, especially for almost all of undergrad lectures. We assume everything deterministic, stationary, linear, and homogeneous. And these assumptions bring error and uncertainty. So you have to be careful. So physics is a subset of conceptual world, and they are both subset of the discrete world. So mathematical solution may not be your physical solution, or your discrete solution may not be your mathematical solution. So it's your task as an engineer to seek the physical solution in the discrete environment. When it comes to electromagnetic engineering, as I said in the beginning, now we are surrounded by electromagnetic waves. We carry electromagnetic devices, Bluetooth devices, cell phones, all these equipment. So they all generate either desired or unwanted electromagnetic signals. And we have systems from communication, remote sensing, to defense, to agriculture. And the frequencies vary from DC to terahertz, even above. And the sizes of the systems we are creating, we are designing, we are using, vary from nanometers small, 10 to the power minus 9 meters, to kilometers wide. For example, if you want to communicate with your frigate on the ocean a few thousand kilometers away, then you need maybe 2 to 3 kilometer wide antenna array established on the shore and using the frequency as low as possible. And almost all of these systems today are broadband and digital, and they have to operate close to each other. So we have severe electromagnetic interference and compatibility, EMC, problems. That's why we have witnessed the transformation from simple engineering electromagnetics to today's complicated electromagnetic engineering. So instead of calling microwave, radar, biomedical, EMC, antenna propagation, 4G, 5G communication, very large-scale integrated systems engineering, today we prefer to call it electromagnetic engineering. It covers almost everything. And these are some subtitles which are critical under electromagnetic engineering, and they are interrelated. So, for example, if you want to design a multi-sensor integrated system, which I am going to show you a few slides about a challenging problem, you need to well understand all these subtopics. You need to well understand how electromagnetic waves are created, antenna, beamforming, beam steering capabilities, how electromagnetic waves propagate in different environments, how they scatter, how they interact with objects and scatter. All these are critical in designing one simple multi-sensor integrated surveillance system. Let me show you one example. Suppose you are the Prime Minister of Italy. Okay, we are in Italy, so we choose country as an Italy, but maybe Greece, Turkey, China, United States, any country near or on the sea. So you, as a Prime Minister, you call your Science and Technology Director and give him a task to design a system where all surface and air activity around your country, around Italy, will be given continuously on the screen of the computer, let's say Prime Minister's computer or Chief Commander's computer. So the mission is to detect and track every target around a given country, okay? So these are the questions you should ask yourself and answer before even starting conceptual design of such system, okay? What type of sensors, what type of radars are you going to use? How many sensors will you use? If you use less number of sensors, less than enough, then there will be a performance problem. If you use more than enough, then the system will cost more. What will their optimum locations be? Okay, suppose you have 10 sensors. Which are the optimum locations to cover the whole country? Will you plan any other communication systems? How will you satisfy continuity and reliability? And the most critical question, how will you measure the performance? How will you define a performance criteria for such complex electromagnetic problem? So let's say you are going to use HF radar with that coverage. Okay, the yellow area is the coverage range and cross range in that region. So you want to put one in near Lecce to cover that region. HF is 3 megahertz to 30 megahertz. So the wavelength is 10 meter to 100 meters. And are you going to use second HF or third HF sensors? And are you going to use microwave sensors, gigahertz frequencies with wavelengths a few centimeters? And will you design or will you use sensors over moving platforms like aircrafts? If you are going to use aircrafts to satisfy the continuity of the system under all weather conditions, day to night, summer to winter. How many aircrafts will you need? Because before the first aircraft lands, the second one should take off to cover the area. So these are all critical questions. And all these sensors will send you terabytes of data continuously. You need to collect all the data in Operational Control Center, OCC, and then do the signal processing, image processing, detection, tracking, classification, all kinds of software plays. So these are physical challenges, okay, for designing such systems. Propagation, how electromagnetic waves are propagated at different frequencies. So microwave propagation is totally different than HF propagation. C clutter, electromagnetic waves interact with C waves and then generate unwanted clutter. So we have clutter, unwanted signal, okay? We have target and we have noise. So C clutter is very critical. Also ionosphere is very critical because you send signals here, but some of the energy couples up, and 100 kilometers up to 400 kilometers from the ground of the atmosphere is called ionosphere. It's a moving clouds of electrons, okay? And ionosphere, the characteristics, physical characteristics of ionosphere changes from morning to noon to afternoon to midnight, and from summer to winter, and from one sun cycle to another. So sun has a cycle of 10 to 12 years. So at some years, sun gets crazy, sends out magnetic storms, and it affects all communication devices. And at some other years, it becomes quiet, calm. So if you want to understand physical characteristic of ionospheric clutter and to survive under ionospheric clutter, you need to record maybe 50 years or 60 years of clutter data to analyze and to understand physical characteristics. So these are all critical questions. Antenna, frequency band, target RCS, how electromagnetic waves interact with frigates or airplanes, and backscatter or forward scatter. Electromagnetic engineers use signal processing algorithms, maybe more than signal processing society. And at the end, you need fusion, either data fusion or sensor fusion. Are you going to use detection in, let's say, radar level or in the operation control center? These are all critical questions. I was working with Turkish Navy 30, 35 years ago. We have designed such system for Asian Sea, where the sea between Greece and Turkey. You know, Turkey and Greece, we drink ouzo on Sundays. They have ouzo, we have Turkish rakı, very strong, like Italian grappa. And on Saturdays and on Sundays, we drink them. But on Mondays, we start fighting, dog fighting, okay, until the end of that week. So I was working with such system for Turkish Navy, and Canadian government established two HF radar system in 1995, 1996, more than nearly 30 years ago, in that region. So this region is rich in terms of oil reserves. Canada is digging oil in that region. And this is the extension of that region. So they put two HF radars with overlapping coverage. And here they have these oil platforms. So they use these oil platforms to dig petroleum, oil in this region. And their enemy For example, for Turkish system, our enemy was Greek frigates, okay, behind the islands. But Canadian system's enemy was icebergs coming from north. Because of global warming, if a huge iceberg hits one of the oil platforms, the economy of Canada may be severely damaged or affected maybe 6 months or up to 2 years, even more. So they want to detect icebergs coming from North Pole as early as possible, as far as possible, so they can get rid of those icebergs. This video, maybe 25 years old, showing the real data with Canadian government. They invited me to join there. I spent 2 years with Raytheon Canada at that time. They have real system. I did all the numerical simulations for Turkish Navy. So we find real data with our simulation experience and try to solve some unexpected problems during early stages. So you are observing dots moving in that video, okay? Each dot supposed to represent one ship in that region, okay? Are you sure each dot is a real ship in that region? Maybe just computer-generated ghost data, 1 pixel, okay? So how do you test such system? How do you do performance tests of such systems? For example, let's focus on one of the targets here. So this is the target. This is 100 kilometers. And this is the signal environment which you do the detection. This is range. This range. This is Doppler velocity axis. And the colors represent dB, 100 dB, the most amplitude ones. And this dark blue represents noise floor, no signal, okay? So how do you do detection? 100 kilometer here corresponds to this one. So your ship is only a point on this scale, and the amplitude of the ship, backscatter energy of the ship, is like this one, okay? So it is maybe 80, 90 dB lower than sea clutter and ionospheric clutter. How do you do the detection? So if you draw this one in two-dimensional space, you get this signal environment, power versus velocity, Doppler frequency. So this is the noise floor. We do detection with using constant false alarm rate, we call CFAR. And you just choose a threshold. Below threshold, no target. Above threshold, you decide there is a target, okay? So if you use very high CFAR detection, you may lose the target. If you lower it, then you will have many ghost signals. So high frequency surface wave radars, they operate in a very high false alarm rate. So these are Bragg echoes. So it's very critical to do the detection. So this slide shows you all detected targets in, let's say, 20 minutes or half an hour, okay? All detected targets. You observe maybe hundreds of targets, but in reality, there are only 5 or 6 ships at that time. But after detection, during the tracking phase, you can say that, okay, this may be a ship moving with a constant speed. Another one may be that one, that one. So even this sensor works or operates in very high false alarm rate. If you know the physics, how to get rid of unwanted clutter, how to get rid of noise, you can still survive under very high false alarm rate. So classification, identification, even threat evaluation stages, you can process signals and get the tactical picture as realistic as possible. So all these problems, including what you have heard from the other distinguished lecturers today, these are the 4 keywords under electromagnetic theory. Radiation, how electromagnetic waves are radiated, created by antennas. Then propagation, how electromagnetic waves travel from point A to point B in different environment, how they interact with objects and scatter, and under scattering, diffraction is very critical. So I'm going to show you a few video clips showing that on your this part left, you should observe total fields. Here, scattered only fields. So this line, black line, is a perfectly electrical conductor strip, infinite in this direction. So you are observing 2-dimensional scattering in terms of total fields and scattered fields. So a plane wave is coming here. If you look at the total fields, you have shadow region behind the object. If you subtract incident field, you show this one, you see this one, this is scattered fields. So you have strong specular reflection and forward scattering. If you change the angle of illumination, again, total fields and scattered fields, you see you always have strong forward scattering component. And if you look at the edge illumination, again, total fields, scattered fields, but just look, we have soft, hard boundary conditions on the strip. So on this side, we have transverse electric. On the other side, transverse magnetic boundary conditions. So boundary conditions are different on both sides of the strips. So visualization is a good way of understanding physics behind electromagnetics. So these are some screen captures, soft boundary condition, hard boundary condition, and this is incident field, plane wave. This is scattered field, and that's total field. Again, incident, scattered, and total fields. You can visualize how edges of the strips here and there, they create diffraction. So sharp boundaries like this one, this is edge, this creates diffraction. And tip is the intersection of 3 layers. Tip also cause diffraction. They act like secondary sources. So this is the summary. Total field is the addition of incident and scattered field. Under scattered field, we have reflections, refractions, and diffractions. And if you can subtract incident field, you can visualize, observe scattered fields. If you can subtract from the scattered fields reflections and refractions, you can visualize diffraction-only fields. Mathematically, we have been doing this with high-frequency asymptotics, like geometric optics, physical optics, PTD. Can we do the same numerically? We have done this in the last 15 years, published many papers. This is another video. We have a line source, obstacle. This is the shadow region. Line of sight separates shadow region with the interference region. Actually, diffraction has been known for many centuries, since Grimaldi, 1665. So this is the transmitter. If you put your receiver behind the object, you have only diffracted fields. And the color of these waves shows the amplitude of the signal. So if you have strong incident and reflection fields, dark colors represent high amplitude, light color represents low amplitude. So if you have reflections, incident fields, and refractions, you don't need to worry about diffractions. But usually we don't have incident fields, we don't have reflections and refractions, only we have diffracted fields. So this is how we can generate numerical techniques to extract diffraction fields. I'm not going to go into details. These are time domain screen captures. At later incident, we have reflections. Then we have also diffractions in the time domain. So if you want to separate diffraction on the field, you can apply what we call three-step scenario. Wedge problem. You have a wedge, a line source there. Those number of dots represent receivers. So you do the numerical simulations in the time domain for wedge. You have everything there. Then replace the wedge with infinite plane. And you only have incident and reflections, no diffraction. And in the third case, you have only free space problem, only incident fields. So subtract one from the other, you end up time domain diffractions. You do the Fourier transform and get the frequency response of diffracted fields. So this is one example showing the total fields. On the left, total fields around the wedge. And if you subtract incident and reflected fields, you observe only diffracted fields on the right. So diffraction usually accumulates along critical angles. This is a critical angle of incidence. This is a critical angle of reflection. You see, we have strong diffractions along critical angles. Okay, the second part, in 10 minutes, I'm going to end up, but if any of you say, I am sick of listening electromagnetics, just raise your hand. We have an emergency button there. We just press that button and jump to the conclusions, okay? Don't worry. Okay. I usually travel with my girlfriend during my workshops, presentations. She is a psychotherapist in Boston. So whenever you require therapy after 1 hour electromagnetic lecture, she was there with me for you. Okay, so electromagnetic theory, actually, when I was a student, I used to hate electromagnetics because they didn't teach us the physics behind electromagnetics. Only divergence of this vector is equal to rotation of another one, vector algebra. Once you know the physics behind mathematics, everything is beautiful in terms of Maxwell's equations. So here in differential form, here in integral form, okay? Differentiation is nothing but subtraction. Integration means accumulation, so addition. So all you need is two types of operations, subtract or add, okay? And these are the guys who are responsible generating all kinds of electrostatic and magnetostatic and electrodynamic fields, charge density and current density. So they create electromagnetic waves, including static fields. And any environment, any material can be represented electromagnetically in terms of epsilon, mu, and sigma, dielectric parameters, magnetic parameters, and conductivity, heat, loss. And give me your source, give me the material. I will use those two equations and will give you electromagnetic fields. So life is easy once you understand physics. Maxwell's equations are general. They give the solutions of antenna, propagation, scattering, diffraction, whatever your problem is. But once you state your boundary conditions, it will give you the solution of on your problem. If you are lucky, mathematical exact solutions can be found. But in reality, maybe less than 1% of the problems have mathematical exact solutions, and they belong to highly simplified, highly idealized geometries. But mathematical exact solutions are very valuable because we use them in calibrating our measurement devices and measurement environment. Usually we have analytical approximate solutions, what we call high frequency asymptotics. And in the last couple of decades, we have numerical simulation capabilities also. All kinds of problems, electromagnetic problems, can be grouped into four. antenna and radiation problems, propagation problems, scattering problems, and also guided wave propagation problems. We start with Maxwell's equations and apply boundary conditions, but follow different routes. For antennas, we use auxiliary scalar and vector potentials because they are in parallel with the sources. For wave propagation problem, instead of using two first-order coupled Maxwell's equation, we use wave equation, second-order Helmholtz differential equation. For RCS, we know the incident field, so we focus on the scattered field around any object. For the guided wave propagation problems, like cables, connectors, waveguides, man-made, or we have natural waveguides in the atmosphere, we use longitudinal and transverse decomposition of Maxwell's equation. The transverse one will give you eigenvalue problem, the characteristics of the environment, source-free solutions. The longitudinal one, what we call usually is Green's function, that will give you the result of excitation, the source-dependent problem. These are high-frequency asymptotics. The first three are ray-based, and PO and PTD are source-induced current-based models. And these are well-known time and frequency domain numerical simulation techniques. FDDT, TLM, method of moment is the oldest one, parabolic equation, and finite element. So if you do modeling and simulation, this is the chart of the definitions. You have real-world problem. You choose one or two equations, a conceptual model. You do conceptual validity through physics-based analytical modeling. Then you are sure that this set of equations represent your problem. Then you write your computer code. You do the code verification through computer programming. At the end, you get a number from this program. So you need operational validity, either using numerical or physical experimentation. And if you do numerical simulation, VVNC, validation, verification, and calibration are critical. And calibration asks whether the result is tested against a reference data. But in reality, we don't have reference in most of the times, maybe all of the times. So we have to assume something as a reference in that case. So these are some of the electromagnetic virtual tools that we have developed. Maybe some of them are older than you guys, young guys, 30 years old. Propagation, microstrip design, plane waves, antenna beamforming, diffraction, scattering, even transmission lines. And they are free. They are used in many universities, especially for undergrad lectures, all around the world, from China to United States to Europe. We also have some sophisticated simulators. This is one example. It gives you RCS of any given object, three-dimensional object, and it uses two types of techniques, FDDT in the time domain and method of moments in the frequency domain, and compare results. So all you need is to give us your choose target, give us this one. This is a graphics file in any format. Then our tool generates these discrete models. This is the discrete model of FDDT. This is the discrete model of method of moments. So give me a target. We create those two, and then observe electromagnetic scattering around object. For example, here you see a DC-10, number of receivers. You send a plane wave. It's a plane, but in time it's a short pulse, so it's a broadband response. So what you observe here around the object, record, is only a few picoseconds time domain response. So what you need, record transients, apply Fourier transform, and get RCS in the frequency domain, because almost all of the parameters that we are using in electromagnetic engineering, like path loss, insertion loss, refractivity, scattering, anything, they are defined in the frequency domain. Then you obtain these type of polar diagrams. So this is the object, this is the radar direction. These are lower frequencies, these are higher frequencies. Still, just observe these forward scattering components. So there is always a strong forward scattered components, okay? If you can focus on these forward scattered case, you can easily capture low visible targets. Here we have two types of aircrafts. This is what we call low visible stealth aircraft. This is a regular B-21 bomber. And if you nose illumination, then there is a difference in their scattering. But if you send top illumination, because of their geometries, they almost give similar scattering effects. So the beautiful part of modeling and numerical simulation is that once you calibrate your software, you can play what-if type games. What if I play two planes side by side, one on top of other? So this is the result, for example, RCS, scattering versus frequency. The red one is single F-16. The dash blue one belongs to two F-16s. You see, it's very complicated. At some frequencies, for example, two F-16 will give you less scattering effect. At some other frequencies, more, less, more, less, more. So it's very complicated. So there is no single way to predict, let's say, from low frequencies to high frequencies or the opposite. You have to do measurements, simulations at every single frequency because interaction is very complex. You can also use metamaterials. You have already observed some of video clips from previous distinguished lecturers. Here we have a line source. This is double positive and 2, refracted -1, -2, -3. So these are metamaterials. And you see how electromagnetic waves travel through double positive in the forward direction, but you see how in the backward direction. So the phase is moving backwards, this one. Another example, double positive, double negative materials. We have line sources here and here. So autofocusing effect, especially this is critical in reducing the sizes of lenses. Another example, this one, we have a metamaterial layer. So how focusing on the other side of metamaterial. Also, this is last example. Dr. Özlem already showed you this one. So this is a Gaussian pulse coming here direction. If this were double positive regular material, so it should go this way, Snell's law, but inverse Snell's law applies, and then another one applies. So you can play all kinds of simulation games for metamaterials, double positive materials, etc. And the conclusions. So we are surrounded by electromagnetic waves. Computer capabilities have revolutionized how electromagnetic engineering can be taught. Modeling and simulation, VVNC, are crucial. We need to well understand physics behind mathematics and then do the simulations. Always keep in mind the assumptions and validity ranges. If there are more than one technique, that means none of the techniques are global. They have validity ranges, they have advantages and disadvantages. We need to look at the object as a whole, but also pay attention to every details because critical information usually comes from details, and some of scientists who pay attention to details, they receive Nobel Prize. The others become regular professors. In engineering, we don't have Nobel Prize, but we have fellowship, IEEE fellowship, and we have many fellows here. We are lucky. Also, multiphysics has become essential. For example, if you want to design a chip, like computer chip, you have to use electrodynamics together with thermodynamics, because the temperature of that chip during operation may be as high as 200 centigrade Celsius, okay? So the cooling is number one problem before electromagnetic issues there. Artificial intelligence is virtual reality is also, but basic lectures such as measurement techniques should be renewed accordingly. Today's electromagnetic engineering students are very lucky because there are excellent commercial packages and measurement devices, but also they are very unlucky because there are excellent commercial packages and measurement devices. So who is going to be both, you or them? This is the motto I used in my first book, Let's Do It. This is the motto I borrow from Obama, Yes You Can, in my second and favorite book. And this is the motto of IEEE. Tell me, I'll forget. Show me, I'll remember. But if you involve me, then I'll understand. And that's the end of my presentation. Thank you. Thank you. Yeah. No. Yes. Yeah.
Now it's on. So, you are open for question, I think. Do you have questions? I start with a curiosity. I have seen the very interesting work you did with a Canadian, I think.
Yeah.
So a trick, if someone want to approach your coast, is to stop sometimes.
Yeah.
Because if you go and then stops, you cannot see the track they do. Is that correct?
Yes, but still, if you know the propagation characteristics of electromagnetic waves at different frequencies, you can design your sensor radar in such frequencies that you can still detect, let's say, frigates or ships near the shore, even behind the island. Because, for example, low frequencies like HF frequencies, lower HF frequencies, they follow the structure of the terrain profile from sea, land, sea. So your signal at, let's say, 3 megahertz following the surface waves can detect any target behind objects. So this is one aspect that we use to detect not only ships behind islands, but also stealth aircrafts using HF, skywave HF, using VHF, because they follow also the curvature. And you can easily detect low visible stealth aircrafts, because most of the stealth aircrafts are designed against microwave sensors. So if you know which sensor is best and which direction is best, you can easily detect. For example, Russian S-400 system, they can detect anything, even B-21 US bomber, the latest stealth aircraft. They can easily be detected. So in reality, there is no low visibility if you know how to look at the object, if you know the physics.
Yeah, it's like to see in very different colors. I
Yep,
mean,
yep, yeah.
you know, we are able to see something because of the color, something,
Yep,
and you can use all the color you want in this case
Yep,
with different.
exactly.
You said that it's a 90. I heard correctly. 90 dB below the clutter.
Yes.
That's
Yes.
impressive.
Up to 90 dB.
That's impressive.
Yeah. And we have noise. We can survive under noise conditions, okay? Just signal integration in time may be enough to get rid of noise, because noise is fluctuation. This one, your signal is coherent. So if you, let's say, add 100 detections and get the average, then noise is eliminated and you can pick up the signal. But clutter is coherent like target. So you cannot get rid of clutter by simple time averaging. You can get rid of clutter, ionospheric clutter or C clutter, in the frequency domain if their frequencies are different than target frequencies.
You study the typical frequency of the clutters, and you are able to remove.
So engineers, as I said before, we do optimization. Also, we play games. We play tricks, but intelligent tricks, okay? For example, if you want to get rid of ocean clutter, you double the frequency. But ocean clutter depends on the radar signal with the square root. But target with the frequency itself. So if you cannot separate target with ocean clutter, at this frequency, just double the frequency or triple the frequency.
So you can see the difference.
The target moves this one, but this clutter moves slowly, so you can easily get rid of with filters, for example.
Oh, very interesting.
But they are all depending on what you know about the real world. The more you observe, the more you understand all physical behaviors, you can easily take precaution and do whatever you want. Almost, yes, of course, almost.
Any question from the audience?
So I'm going to leave my presentation. If any of you want to go over the presentation or look at the video clips, just ask Cristiano and get it. So we share everything we have.
Thank you so much. Okay then, if no question from audience, I think we can conclude here.
Yeah.
And I would like to thank again you for organizing this excellent initiative, and then also Paolo for organizing.
You do the organization. So thank you.
Paolo did a lot also with the food and so on, so thank you very much. And I would like also to thank the speaker, of course, that travels a lot to arrive here, and also the attendees, and the attendees are the reason why we are here. So thank you so much, also for resisting so long, because I can understand that, especially for students that are not familiar with all things, let's say, probably it is a little bit...
I'm sorry for not bringing my shrink today. I hope you won't need.
The next time we need. Okay. Okay, so this concludes the session, and thank you again for your presence. Thank you.